On the night of July 15, 1977, astronomer Jerry Ehman, a volunteer of the Search for Extraterrestrial Life project, was scanning radio signals when something unexpected happened. He picked up a very strong and unusual signal. This signal, which lasted for 72 seconds, was 30 times louder than the usual background noise and seemed to come from the direction of the constellation Sagittarius. The data was then translated by a computer into a series of letters and numbers, resulting in the sequence 6EQJ5. When Jerry saw the printout the next day, he was so amazed that he circled the sequence and wrote "wow" next to it. This simple reaction gave the signal its name, the wow signal. Experts concluded that the signal source was broadcasting in a regular pattern, somewhat like the rotating beam of a lighthouse. It's as if we only managed to pick up the signal when it was directly aimed at us, and then lost it as it turned away. Despite all the monitoring and analysis done since then, the wow signal remains one of the strongest pieces of evidence, and its origins continue to be widely debated and researched. Whether it was actually a message from aliens or not is still a mystery. Scientists believe that what we detected as the wow signal might not have been the full transmission. Instead, it could have been part of a repeating signal. To understand why we didn't catch the whole thing, we need to look at how the telescope worked. The wow signal was picked up by the Big Ear telescope at Ohio State University, which was built specifically to search for extraterrestrial signals. The telescope was huge, about the size of 3 football fields, with a large mirror that captured signals and bounced them towards smaller mirrors. These mirrors then directed the signals to 2 receivers for analysis. However, the way the Big Ear telescope was built made it hard to consistently pick up the signal. After it first detected the wow signal, there was a few-minute delay before the second receiver could check the same area of space. By that time, the signal was gone. This gap in detection is a big hurdle when trying to confirm where the signal came from. The design and operation of the Big Ear telescope show how the structure of such equipment can affect our ability to confirm signals. If the telescope could have monitored the same spot continuously or quickly revisited it, scientists might have been able to see more signals from the same region in the Sagittarius constellation. This could have provided clearer evidence of where the signal was coming from. The limitation here shows just how important the telescope's design is when it comes to searching for signals from other civilizations. The Big Ear wasn't like traditional telescopes that use mirrors to capture light. It was a radio telescope that used wireframe capture dishes to detect radio frequencies, which are invisible to our eyes. Unlike modern telescopes that can turn in all directions to scan the sky, Big Ear could only tilt its reflector up and down, limiting it to observing a narrow strip of the sky at a time. This design was chosen because it was simpler and cheaper to build than more advanced systems. To overcome this limitation, the designers found a clever way to increase its range. By relying on the Earth's rotation to move the telescope left and right, and adjusting the reflector to cover different angles, Big Ear could eventually observe any point in the sky. This use of the Earth's natural movement was a smart way to make the most out of the telescope's limited mobility, allowing it to cover more ground despite its restrictions. But there was still a downside. Because the telescope relied on the Earth's rotation, it couldn't keep track of the same spot in the sky for very long. This means it might have missed additional signals coming from that region. Picture an entire orchestra of signals being sent from that spot after the wow signal. but Big Ear only caught a brief note from what could have been a much larger broadcast. Space is incredibly vast, and resources are limited, so they have to be strategic with their equipment. They can't afford to dedicate one telescope to watching a single spot for years, hoping for a reply. Instead, they scan large sections of the sky to cover as much area as possible. This approach is like casting a wide net in different locations rather than waiting in one spot indefinitely. By constantly moving and scanning, they increase their chances of picking up signals, even if only for a moment, which is more realistic given the challenges in finding where and when a signal might show up. Searching for alien signals is more complex. Unlike fish, which can be drawn to or scared away by certain things, alien signals aren't affected by our attempts to detect them. While sweeping a telescope across the sky might seem random, it's a practical approach given the vastness of space and the uncertainty of where a signal might be. However, this approach has its difficulties, especially when it comes to follow-ups. Over the years, radio telescopes like Big Ear have picked up several strange, short-lived signals similar to the wow signal, quick bursts of radio waves that we still don't fully understand. The main issue is that without continuous observation and dedicated studies on these signals, they stay mysterious and are often overlooked. Without proper follow-up, we may miss out on crucial data, leaving us with weak conclusions about where these signals come from. This leads to an important idea. The reason we haven't found signs of intelligent extraterrestrial life could be largely due to how we search for it. Of course, this is just one possible explanation. In this discussion, we've talked about some of the technical challenges in detecting alien life. But there are also many other theories that are more speculative and touch on deeper questions about our place in the universe and the nature of other civilizations. These theories open up interesting possibilities about what life beyond Earth could be like. If you enjoyed this topic, stay tuned for future videos where I'll dive into these speculative ideas, offering more insights into the search for alien life. The question of whether aliens are out there watching us from the stars is both exciting and complicated. The enormous number of stars and galaxies in the universe suggests that the conditions for life, including intelligent life, could be common far beyond Earth. If even a small percentage of planets around these stars are capable of supporting life, then life might be widespread in the cosmos. There are many possible reasons why we haven't made contact with other civilizations yet. One reason could be the vast distances between stars, making communication and travel across space extremely difficult. Another reason might be timing. Civilizations could rise and fall at different times, missing the chance to connect with each other. Another important factor is the way communication happens. Advanced civilizations might use technologies or methods that we don't yet understand or can't detect. It's also possible that they choose not to contact us, possibly observing us from a distance like how we study less developed species on Earth. The wow signal, a mysterious signal detected in 1977, highlights both the potential and the challenges in searching for alien life. Despite many attempts to find it again, the signal remains unexplained and continues to spark curiosity and debate. It reminds us just how much we still need to learn about the universe and where we fit in it. In the end, the search for extraterrestrial life is driven by our natural curiosity and a deep need to answer one of the biggest questions we've ever asked. Are we alone in the universe? Whether or not we make contact within our lifetimes, the pursuit of this knowledge pushes the boundaries of human understanding and exploration. If we do ever make first contact, it will undoubtedly be a moment that changes human history forever. What happens next? What would it mean if we received and confirmed a signal from aliens? How would it change our lives, our priorities, our view of the world, and even our own sense of identity? Would we be ready for such a discovery? SETI's main goal is to find a clear, repeatable signal from space, like the famous WOW signal. To prove we're not alone in the universe, we would need to detect such signals more than once. To actually communicate with aliens, we would either need to send them a message and wait for a response, or they would need to reach out to us first. We could also try sending spaceships or robotic probes. But with our current technology, space travel is incredibly slow. For example, it took the Voyager 2 probe about 49 years just to leave our solar system. To reach the closest star system, which is 4 light-years away, it would take more than 81,000 years at the speeds we can currently manage. That's the equivalent of 2,700 generations of humans. So unless our closest alien neighbors are right next door at that nearest star, making contact would be extremely difficult. Even if we develop better spacecraft, reaching the speed of light is nearly impossible. It would require more energy than we can ever hope to gather, more than what's available in the entire universe. That means traveling at light speed isn't realistic, which limits how far we can go. But there's still a possibility. Some scientists are exploring concepts like wormholes that could bend space itself. This might let us travel faster than light without breaking the laws of physics, because the speed limit only applies to moving through space, not to moving space itself. For now, sending messages through space, like radio signals, is much easier and cheaper than sending spaceships. It's kind of like making a phone call instead of visiting someone in person. It saves a lot of time and effort. If we ever do connect with aliens, it will most likely start by us picking up one of their calls. Even though the speed of light is incredibly fast, about 300 million meters per second, it's still the fastest way any signal, like light or radio waves, can travel. This speed limits how quickly we can communicate across the huge distances in space. If we want to talk to aliens, any message we send has to travel through space to reach them. Then, if they answer, their reply is to make the long trip back to us. So there's a big delay in communication. We only began using radio technology in the mid-1890s, so we haven't been doing this for very long. Because of this, we'd only be able to exchange messages with aliens living at most 60 light-years away from us. That's 60 years for a message sent out around 1900 to reach them, and another 60 years for their reply to get back to us. Have you ever wondered how the universe got to a point where we can't find its edge, stretching billions of light years across? To answer that, we need to go back to the beginning of the universe. The answer might be there. One of the biggest questions in cosmology is, how did the universe start? The most widely accepted idea is the Big Bang theory. This theory explains how our universe began and grew. Picture every star, planet, and galaxy squeezed into one incredibly hot and dense point. Scientists think this is how it all started about 13.8 billion years ago. From this tiny packed point, the universe began to expand and cool. This event, called the Big Bang, set the universe on the path of growth that led to the vast distances we see today. The term Big Bang can be a bit confusing because it sounds like an explosion in space. But it wasn't an explosion in space, it was the rapid expansion of space itself. In the first tiny fraction of a second after the Big Bang, the universe expanded incredibly fast in what's known as cosmic inflation. During this short time, the universe grew from something extremely small to something we could see with the naked eye. As the universe expanded, it cooled down enough for energy to turn into particles of matter. These particles came together to form simple elements like hydrogen and helium. Over billions of years, gravity pulled these elements together to form stars, galaxies, and planets. The formation of these elements happened within minutes of the Big Bang, as the universe cooled enough for protons and neutrons to create atomic nuclei. There's a lot of evidence backing the Big Bang theory. One key piece is the cosmic microwave background radiation, which is like a leftover glow from the early universe. This radiation gives us a glimpse of the universe just 380,000 years after the Big Bang. Before that, the universe was so hot and dense that light couldn't move freely. The evenness and tiny variations in the CMB support the idea of cosmic inflation and the fast expansion of the universe. Another important piece of evidence is the redshift of galaxies. This redshift shows that galaxies are moving away from us, proving that the universe is expanding. Edwin Hubble first noticed this in the 1920s. The farther away a galaxy is, the faster it's moving away from us, which supports the idea that the universe was once much smaller, hotter, and denser. While the Big Bang theory explains how the universe expanded and evolved, it brings up more questions. For instance, it doesn't explain what lies beyond the observable universe. The theory of cosmic inflation talks about rapid expansion right after the Big Bang, but it doesn't answer what's beyond what we can see. Before scientists discovered the cosmic microwave background radiation, there was a different idea called the steady-state theory. It claimed the universe had no beginning or end and stayed the same overall, even as it expanded by constantly creating new matter. This theory was popular in the 1940s but lost support after the discovery of the CMB in 1965, which strongly supports the Big Bang theory. Other ideas, like the cyclic model, suggest the universe goes through endless cycles of expansion and collapse. After the Big Bang, the universe expanded and cooled. At first, it was a hot, dense mix of particles. As it expanded, it cooled enough for these particles to come together and form the first atoms. These atoms then clumped together to create the first stars and galaxies. The universe is still expanding today, with galaxies moving away from us in all directions. If we look even further back, the first long-lasting particles, protons and neutrons, which make up atomic nuclei, appeared about 1/10,000th of a second after the Big Bang. Before that, there wasn't any material as we know it. Physics can even take us back to processes that happened before stable matter existed. The observable universe includes all the matter and energy we can see from Earth, limited by the speed of light and the age of the universe. Since the universe is about 13.8 billion years old, we can only see light that's traveled up to 13.8 billion years to reach us. However, because the universe is expanding, the observable universe stretches much farther than 13.8 billion light years. The radius of the observable universe is believed to be around 46.5 billion light-years, making the diameter roughly 93 billion light-years. Despite the enormous size of the observable universe, it's only a small part of the whole universe. The actual size of the entire universe is unknown and could be infinitely larger than what we can observe. The expansion of the universe means that objects at the edge of what we can see are moving away from us faster than the speed of light, making it impossible to observe anything beyond this point. The universe has been expanding ever since the Big Bang, and this expansion impacts how we see things. Galaxies are drifting apart, and space itself is stretching between them. Because of this, the observable universe is always growing as light from farther regions finally reaches us. Within the observable universe, scientists estimate there are about 2 trillion galaxies, each holding billions of stars. These galaxies vary in shape and size, from spirals like our Milky Way to elliptical and irregular forms. The vast number of stars suggests that there could be countless planetary systems, some of which might have conditions suitable for life. One of the most striking images taken by the Hubble Space Telescope is the Hubble Deep Field, which shows a tiny patch of sky filled with thousands of galaxies. Each of these galaxies contains stars, planets, and possibly even life. This image represents just a small slice of the sky, reminding us of the huge number of galaxies in the observable universe. To understand how the universe could emerge from nothing, we need to look into quantum mechanics. In quantum physics, nothing isn't really empty. It's more like a state of vacuum energy where particles constantly appear and disappear. This is known as quantum fluctuations. Quantum fluctuations happen in what's called the quantum vacuum, a state with the lowest possible energy where particles can briefly appear before vanishing. According to quantum mechanics, it's possible for these fluctuations to give rise to an entire universe. In this context, nothing is actually an energetic state capable of producing matter and energy. One key idea in this process is Heisenberg's uncertainty principle, which says that certain properties, like position and momentum, can't both be known precisely at the same time. This principle allows for the temporary creation of particles from the vacuum, as long as they disappear quickly enough to avoid breaking the law of conservation of energy. Quantum fluctuations cause particles to appear and disappear in an instant. While this sounds strange, these particles have been observed in experiments. The vacuum of space is filled with particles popping in and out of existence, showing that the quantum vacuum is more like something rather than nothing. Where did space and time come from? To answer that, we need to go back to the very beginning, to the Planck epoch. This was a period so early in the universe's history that our current physics theories don't fully apply. It happened only a tiny fraction of a second after the Big Bang. During this time, both space and time were influenced by quantum fluctuations. Usually, physicists use quantum mechanics to study tiny particles and general relativity to study large-scale objects like stars and galaxies. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines both approaches. We don't have a perfect theory of quantum gravity yet, but ideas like string theory and loop quantum gravity offer some possibilities. These theories suggest that ordinary space and time arise from deeper microscopic processes. What we experience as space and time is the result of quantum processes that are difficult for us to grasp because we're used to the large-scale world. Quantum fluctuations happen all the time, even in what we think of as empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist briefly, and then annihilate each other. This process is known as quantum foam. But quantum fluctuations alone don't explain the universe's size and complexity. There's also dark energy, a mysterious force that fills space and accelerates the expansion of the universe. While we don't fully understand dark energy, it's thought to play a major role in shaping the universe. So, how did we go from quantum fluctuations and dark energy to the massive, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred just fractions of a second after the Big Bang. During this short period, the universe expanded exponentially, setting the stage for the formation of galaxies, stars, and planets. Over time, dark energy caused these celestial objects to push away from each other, leading to the continued expansion of the universe. Dark energy is a mysterious force that works against gravity, causing the universe to expand faster and faster. As galaxies move away from each other at increasing speeds, this could eventually result in a future where galaxies are so far apart that they become isolated from one another, making the universe a much lonelier place. In conclusion, the birth and expansion of the universe involve complex processes driven by quantum mechanics and forces like dark energy. From the Big Bang and cosmic inflation to the ongoing expansion fueled by dark energy, these events have shaped the observable universe we know today. As we continue to learn more about these processes, we're slowly uncovering the mysteries of the cosmos and our role within it. But after understanding how the universe started, we also need to understand how it reached the state we see today. Cosmic inflation refers to a brief moment right after the Big Bang when the universe expanded at an incredibly fast rate. Imagine the universe as a tiny, tightly packed point that suddenly stretched out, growing at an unimaginable speed. This rapid expansion happened in less than a fraction of a second, making the universe much bigger almost instantly. Scientists believe that this rapid growth was powered by a special kind of energy that existed in the early universe. This energy, often called inflationary energy, made space itself stretch faster than the speed of light. It's like blowing up a balloon in an instant, causing it to expand from the size of a pinhead to the size of a basketball. Before inflation, the universe was a chaotic mix with random variations in density and temperature. The rapid expansion spread everything out, creating a smoother and more uniform universe on large scales. Although inflation smoothed out the universe, it also left behind tiny irregularities or fluctuations. These small differences in density eventually grew due to gravity, forming the galaxies, stars, and planets we see today. One of the most important pieces of evidence for inflation is the cosmic microwave background radiation. The CMB is the faint glow left over from the Big Bang and provides a picture of the universe when it was just 380,000 years old. The regularity of the CMB, with its small temperature variations, fits with what the theory of inflation predicts. The way galaxies and galaxy clusters are spread out in the universe also supports the idea of inflation. The sizes and distribution of these structures match the tiny fluctuations left by inflation. The universe seems to be geometrically flat, meaning it follows the rules of simple, straight-line geometry. Inflation explains why the universe is flat, because the rapid expansion would have smoothed out any initial curvature. Inflation also solves the horizon problem, which asks why different parts of the universe, so far apart, have the same temperature and properties. The rapid growth during inflation would have allowed these regions to be in contact before they were spread out by inflation. Inflation is thought to be driven by a theoretical field called the inflaton field. This field, tied to a particle called the inflaton, had a high energy level that caused the rapid expansion. As the universe grew, the energy in the inflaton field decreased, eventually bringing the inflationary period to an end. The energy from the inflation field was then turned into particles and radiation, heating up the universe and leading to the formation of the first elements in a process known as Big Bang nucleosynthesis. During inflation, tiny quantum fluctuations in the inflation field were stretched to much larger scales. These fluctuations created small areas of more and less density in the early universe. Over time, gravity amplified these fluctuations, leading to the formation of large-scale structures like galaxies and galaxy clusters. Cosmic inflation explains several important features of the universe, like why it looks the same in all directions, and why the cosmic microwave background radiation is so uniform. It also explains the flat shape of the universe, as seen in the CMB, and how galaxies and large-scale structures formed from small initial fluctuations. Not only does the inflation theory suggest that the universe expanded rapidly, but there's also an extended version called chaotic inflation theory that explains how the early universe could have experienced an extremely fast expansion. To understand chaotic inflation, let's start with a simple example. Imagine you have a magic balloon that starts out very small, almost too tiny to see. Suddenly, this balloon begins to expand at an incredibly fast rate, much faster than any normal balloon. As it grows, some parts of the balloon keep getting bigger, while other parts stop expanding and stay the same size. This magic balloon is like a special part of space going through what we call chaotic inflation. In this theory, the universe is like that magic balloon. Some areas of space experience rapid expansion, growing exponentially, while other areas remain unchanged. This leads to a patchy universe, where different regions expand at different rates. This patchiness means the universe didn't need a perfectly smooth starting point to begin its rapid growth. It could have started expanding from almost any condition, whether smooth, bumpy, or somewhere in between. Chaotic inflation explains that the universe's expansion could have started under a wide variety of conditions. Unlike standard inflation theory, which may require specific starting conditions, chaotic inflation suggests that almost any patch of space can suddenly start expanding rapidly due to the presence of a special energy field known as the inflaton field. The inflaton field can cause different parts of space to expand at different speeds. In some areas, the inflaton field's energy is high, leading to rapid growth. In other areas, the energy is lower, resulting in slower or no growth. Over time, the regions with rapid expansion take over, creating a universe where certain areas grow quickly, while others remain unchanged. To picture chaotic inflation, imagine the universe as a landscape with hills and valleys. The inflaton field represents this landscape, where the height of the hills and valleys shows the energy level of the field. In some places, the field has high energy, causing rapid growth. In other places, the energy is lower, leading to slower growth or no growth at all. As time goes on, the areas on top of the hills expand rapidly and take over the landscape. These regions keep growing, creating a universe that is both vast and diverse. Chaotic inflation fits into the larger Big Bang theory by offering a way for different parts of the universe to have expanded rapidly after the initial explosion. It complements the standard inflation model by suggesting that this rapid expansion could have happened under a wide range of starting conditions without needing a perfectly smooth beginning. The resulting universe from chaotic inflation could be patchy, with some areas expanding faster than others. This patchiness can help explain the large-scale structure of the universe and how galaxies and clusters are spread out. Chaotic inflation also opens up the idea of multiple universes or a multiverse. Since different areas of space can expand at different rates, it's possible that other universes with different properties exist beyond our observable universe. According to this theory, the edge of the universe isn't a single clear boundary, but a patchwork of regions that expanded at different speeds. Some areas may have stretched so far that they lie beyond what we can currently observe, creating a horizon that keeps shifting as the universe continues to grow. The idea of multiple regions expanding at different speeds also supports the possibility of a multiverse, where other universes with different physical laws could exist beyond what we can see. This makes the true edge of our universe not a clear-cut boundary, but a dynamic and ever-changing frontier. The concept of nothingness or absolute emptiness is something that confuses the human mind. We often think that everything must come from something. So, how did everything begin? We say it started from nothing, but how can nothing turn into something? In the vast universe filled with shining galaxies and black holes that consume matter, the idea of nothingness challenges our understanding of how things work. This isn't just a philosophical idea, it's a key question in cosmology that has fascinated scientists and thinkers for ages. Imagine a region of space with no stars, planets, or any matter, just pure emptiness. It's like a quiet corner of the universe where the usual laws of physics might not apply. The idea of nothingness seems confusing, yet it plays an important role in science and cosmology. To grasp the mysteries of the universe, we first need to understand what nothing means when talking about space. Empty space might seem like a perfect vacuum, totally free of matter or energy. While this view is partly true, it doesn't fully capture the complexity revealed by modern science. In today's understanding, nothingness isn't an absolute void, but a complex, ever-changing environment that goes beyond what we once thought. Let's look at this idea through a scientific lens. Contrary to what many people think, the vacuum of space isn't completely empty. It's full of quantum fluctuations, where particles and their opposites suddenly pop into existence and quickly destroy each other. These fluctuations give the vacuum a lively and ever-changing character. Space is closely tied to the fabric of space-time, as explained by Einstein's theory of general relativity. Even in areas without visible matter, massive objects can bend space-time, affecting the movement of nearby objects. When we look into deep space, we can detect a faint echo from the Big Bang. This is the cosmic microwave background radiation, a leftover from the early universe that shows how space has changed over time. Despite all the knowledge we've gained, the concept of nothingness in space remains a deep mystery for scientists and philosophers. There are theories that suggest certain regions in the universe might have an almost complete lack of matter, although these ideas are still speculative. Some think there could be areas with extremely low matter density, nearing true emptiness. If these voids exist, they might offer clues about the nature of space itself. Is empty space really free of all matter and energy? This simple question opens up a whole world of scientific and philosophical exploration. Traditionally, space is seen as a perfect vacuum, a blank canvas without matter or energy. This idea fits our common view of emptiness, but as we learn more about cosmology, we discover that reality is far more complicated than we ever imagined. In the world of quantum mechanics, which deals with the behavior of the smallest particles, we encounter a concept that challenges our idea of nothingness: quantum fluctuations. These fluctuations suggest that even in the emptiest parts of space, particles and antiparticles can suddenly appear, interact for a moment, and then vanish. These brief events defy our usual understanding of emptiness, making the void seem more dynamic than we thought. Einstein's theory of general relativity also teaches us that space and time are connected as a four-dimensional fabric called space-time. Massive objects like planets, stars, and black holes can bend this fabric, affecting how nearby objects move. So, the idea of a completely empty, unchanging space is more of a dream than a reality. How does the concept of nothing connect with the presence of dark matter, and what does it reveal about the complex structure of the universe? To answer this question, we first need to understand what dark matter is. Unlike the ordinary matter that makes up stars, planets, and galaxies, dark matter is invisible to us. We only know it's there because of the gravitational forces it creates. It represents the ultimate form of nothingness because it cannot be directly seen and doesn't fit the traditional idea of matter. Scientists first realized dark matter must exist by observing how galaxies move. The gravitational pull from visible matter alone couldn't explain their behavior. To solve this mystery, scientists suggested the existence of an unseen, intangible substance, dark matter, that fills cosmic voids and holds galaxies together. The Big Bang theory suggests that the universe began as a singularity, a point of infinite density and temperature about 13.8 billion years ago. This moment marked the birth of space and time from what could be considered nothing in conventional terms. But how does this theory, which describes the explosive start of our universe, connect with the concept of nothing? To understand this, we we need to grasp the nature of the singularity at the moment of the Big Bang. A singularity is a state where the usual laws of physics no longer apply. It's a point of infinite density and zero volume, which defies our normal understanding of matter and space. In this sense, the singularity can be seen as a form of nothingness, a point where the universe had no familiar structure or dimensions. However, this nothingness was filled with potential. As the universe expanded from this singularity, it experienced rapid inflation, causing space to stretch in an instant. The universe quickly changed from a state of cosmic nothingness into a cauldron of energy, particles, and forces that shaped everything we see today. In the first moments of the Big Bang, the universe was extremely hot and dense, like a thick soup of particles and radiation. In just a fraction of a second, it went through several changes, including nucleosynthesis, where the first atomic nuclei formed. This process eventually led to the formation of stars, galaxies, and the complex structure of the universe we observe now. How do we know the Big Bang happened? There's a lot of evidence supporting the theory. One key piece is the cosmic microwave background radiation, which is like the afterglow from the early universe. This radiation gives us a glimpse of the universe as it was just 380,000 years after the Big Bang, before which it was too hot and dense for light to move freely. Arno Penzias and Robert Wilson accidentally discovered this radiation in 1965. The even spread and slight variations in the CM support the idea of cosmic inflation and the rapid expansion of the universe. Another piece of evidence is the redshift of galaxies, which shows that galaxies are moving away from us, indicating that the universe is expanding. Edwin Hubble first noticed this in the 1920s. The farther away a galaxy is, the faster it seems to be moving away, backing up the idea that the universe was once much smaller, hotter, and denser. However, the Big Bang theory also raises big questions. For example, it doesn't explain what happened before the Big Bang or what lies beyond the parts of the universe we can see. It also introduces the concept of cosmic inflation, the rapid expansion that occurred right after the Big Bang. Before the discovery of the cosmic microwave background radiation, the different idea called the steady-state theory was popular. This theory suggested that the universe has no beginning or end and stays the same overall, even though it's expanding by constantly creating new matter. There are also other ideas, like the cyclic model, which suggests the universe goes through endless cycles of expansion and contraction. After the Big Bang, the universe expanded and cooled. At first, it was a hot, dense soup of particles. As it grew, it cooled enough for particles to come together and form the first atoms. These atoms eventually formed the first stars and galaxies. The universe's expansion is still happening today, with galaxies moving away from us in all directions. Going even further back, the first long-lasting particles, protons and neutrons, which make up atomic nuclei, appeared around 1/10,000th of a second after the Big Bang. Before that, there was no matter as we know it, but physics allows us to trace the timeline even further back to events that took place before any stable matter existed. To understand how the universe could start from nothing, we need to explore the strange world of quantum mechanics. In quantum physics, nothing isn't the absence of anything, but rather a state filled with vacuum energy, where particles constantly pop in and out of existence. This is known as quantum fluctuations. Quantum fluctuations happen in what's called the quantum vacuum, a state with the lowest possible energy where particles can briefly appear and then disappear. According to quantum mechanics, these fluctuations could lead to the creation of a universe. So, in this context, nothing is actually an energetic state that can produce matter and energy. A key concept here is Heisenberg's uncertainty principle, which says that certain physical properties, like position and momentum, can't both be known precisely at the same time. This principle allows particles to momentarily pop into existence from the vacuum, as long as they vanish quickly enough to follow the law of conservation of energy. Quantum fluctuations cause particles to appear and then disappear shortly after. This might sound odd, but these particles have been observed in many experiments. The vacuum of space is full of particles constantly being created and destroyed, seemingly out of nothing. This shows that the quantum vacuum is actually more like something rather than nothing. Where did space and time themselves come from? To answer this, we need to look back to the very beginning, during the Planck epoch. This period was so early in the universe's history that our best physics theories don't fully apply. It happened just a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Usually, physicists use quantum mechanics for tiny particles and general relativity for large-scale objects like stars and galaxies. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines both approaches. We don't have a perfect theory of quantum gravity yet, but ideas like string theory and loop quantum gravity offer some possibilities. These theories suggest that ordinary space and time come from deeper microscopic processes. What we experience as space and time results from quantum processes that are hard to grasp because we are used to the large-scale world. Quantum fluctuations happen all the time, even in what seems to be empty space. According to Heisenberg's uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a short moment, and then destroy each other. This process is known as quantum foam. But quantum fluctuations alone don't explain the universe's vast size and complexity. There's also dark energy, a mysterious force that fills all of space and speeds up the expansion of the universe. While we don't fully understand dark energy, it's thought to be crucial in the creation and development of the cosmos. So, how did we go from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe grew exponentially, setting the stage for the formation of galaxies, stars, and planets. In the Planck epoch, our usual ideas about space, time, and cause and effect don't really apply. Yet, all theories of quantum gravity describe something happening in that era as some quantum precursor to the space and time we know. But where did that come from? Even if causality doesn't work the way we expect, it might still be possible to explain parts of the Planck epoch universe in terms of other parts. Unfortunately, our current understanding of physics can't provide clear answers yet. Until we develop a theory of everything, we won't have a definitive explanation. The most we can confidently say is that physics hasn't found any confirmed examples of something coming from truly nothing. In this context, the idea of nothingness becomes dynamic and ever-changing. It's not just an empty void, but a backdrop on which the universe writes its story. A story that began with the explosive birth of the cosmos. The question of whether the vacuum of space is truly empty, without particles or fields, is a key topic in advanced cosmology. At first glance, we might think of the vacuum of space as a completely empty void, a vast area without any matter or energy. However, when we explore the strange world of quantum mechanics, we discover something surprising. The vacuum is not as empty as it might seem. Quantum mechanics, the science that explains how particles behave at the smallest scales, reveals that space is full of hidden activity. In this view, the vacuum is far from silent. It's buzzing with quantum fluctuations. These fluctuations are like tiny ripples on a still pond, happening at a scale much smaller than atoms. In these quantum fluctuations, particles and their opposites briefly appear from the vacuum, interact, and then quickly disappear, like a fleeting dance. These brief events challenge our usual idea of emptiness, showing that even what seems empty is filled with activity. Additionally, the vacuum of space is not just an empty stage, it's an essential part of the universe. It contains fields that control the fundamental forces, like the electromagnetic field, which stretch across all space, even in places that seem empty. In advanced cosmology, it becomes clear that the vacuum is far from a true void. It's an active space where the line between nothing and something is blurred, alive with the constant movement of particles and fields that make us rethink what emptiness really is. This idea isn't just theoretical, it has real-world applications. Scientists can tap into the energy within these quantum fluctuations through something called the Casimir effect. When two parallel plates are placed close together in a vacuum, they experience a tiny but measurable force pulling them together because certain vacuum fluctuations are suppressed between them. This effect, though very subtle, shows how nothingness in the vacuum can have real physical effects. To truly understand how something could come from nothing, we first need to explore several interpretations of what nothing means. In the first interpretation of nothing, it refers to a state where the basic building blocks of everything we see are missing. Imagine a universe with no galaxies, stars, planets, or even humans. Everything we interact with is made up of tiny subatomic particles. These particles are the building blocks that form our universe. If we start with a universe full of matter, we can see how it evolves, cools down, and is shaped by gravity into the universe we know today. Stars go through life cycles, creating heavier elements that lead to the birth of new stars, planets, organic compounds, and eventually life. But here's a big question. How did we end up with a universe filled with matter and not one with equal amounts of matter and antimatter? This is one of the biggest mysteries in physics. The universe is made almost entirely of matter, with very little antimatter. Every star, planet, and galaxy we've observed is made of matter. So how did this imbalance happen? This problem is known as baryogenesis, the process that created more baryons than antibaryons in the early universe. Scientists have many ideas, but we still don't have a definite answer. We don't know why there's more matter than antimatter instead of an equal balance. In the second interpretation of nothingness, nothing is the emptiness of vast space. You might think of nothing as truly having no things at all. If that's the case, then the first interpretation doesn't fully fit because it still involves something. To really get a sense of this version of nothingness, imagine removing every basic element of matter. This means taking away every single particle and all forms of energy. If we could do that, what would be left? Just an empty space, no particles, no matter, no radiation at all. This is what some scientists see as the true scientific meaning of nothingness. Even in this scenario, space-time still exists, following the principles of general relativity. The speed of light and the gravitational constant still have their values. And most importantly, there's something called zero-point energy. Even in the emptiest space, there's a tiny amount of energy. Today, we recognize this as dark energy, which is causing the universe to expand. But even in this very empty situation, some key aspects still remain. The laws of physics are still there. Quantum fields, like the electromagnetic field, gravitational field, Higgs field, and fields related to nuclear forces still exist. So, even with no matter or radiation, this version of nothing still gives rise to an interesting universe. It's fascinating to think that even when everything we see is gone, the universe can still be a dynamic and captivating place. The third interpretation of nothing considers it as the lowest energy state possible. Right now, our universe has something called zero-point energy, which is a tiny amount of energy that exists everywhere in space. We don't know if this zero-point energy is the absolute lowest energy possible, or if there's an even lower state we haven't found yet. There's a chance we're in a false vacuum state, with the true vacuum or the lowest energy state still out there, either close to zero or even lower. If the universe transitions from this false vacuum to a true vacuum, it could trigger a catastrophic event known as vacuum decay. This would drastically change the universe. Light particles would gain mass, the electromagnetic force would become limited to short distances, and most of the sunlight wouldn't reach Earth. Thinking of nothingness as the ultimate lowest energy state means imagining a situation where all matter, energy, radiation, and any distortions in spacetime are removed. What remains is a state of perfect emptiness, but with the laws of physics still in place. This ultimate low energy state would make it impossible to generate any work, energy, or particles from it. However, some might still consider this something because space-time and the laws of physics would still exist. In this state, there would still be a backdrop for events, but without anything actually happening. It would be like a stage with no characters, storyline, or setting, just an empty space. Imagine reaching the universe's true foundational state, whatever that might be. In this state, all matter, energy, and any distortions in spacetime would be gone. What's left would be the ultimate material emptiness. This ultimate low energy state wouldn't allow for any creation of work, energy, or particles. Yet, some might still see it as something because space-time and the laws of physics would continue to exist. So, our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the framework of space-time and the laws of physics remain. It's another incredible mystery that keeps scientists exploring and searching for answers. This is the most extreme interpretation of nothing. It's the idea that true nothingness only happens when the entire universe, including its laws, completely vanishes. This concept goes beyond our usual understanding of reality. Imagine taking away everything, not just matter and energy, but also space, time, and even the laws of physics. This kind of nothing is beyond what physics can describe because it represents an absolute void where literally nothing exists. From a physics perspective, this idea is difficult to grasp. How could something like spacetime exist if there's no space or time? How could the laws of physics work if there's no framework for them to operate in? This kind of nothing is nearly impossible to comprehend and may not have any real-world meaning. Thinking about this ultimate nothingness raises many questions without clear answers. For example, how could space and time begin if neither existed before? Is it even possible to have something without space or something beginning without time? Imagine an absolute void, a complete absence of everything. From a physics standpoint, this suggests a state beyond the limits of space and time, from which our universe and its laws might have emerged. But we're not sure if this idea is meaningful or just a product of our imagination. This concept brings up challenging questions. For instance, how could space and time start in a state where neither exists? Can we even imagine something existing outside the universe without space or beginning without time? Where would the rules that govern particles and forces come from? While this idea of nothingness seems complete in a philosophical sense, it might not have any practical substance. It could simply be a way for us to try to understand things that are beyond our reality. When scientists talk about nothing, it's often assumed that everyone has the same idea of what nothing means. But that's not always true. Different people and different contexts can change how we think about nothing. While scientific theories about nothing are based on principles and observations, the study of the cosmic microwave background radiation gives us insights into the early conditions of the universe. Detailed measurements of the CMB have helped us understand the universe's age, composition, and structure. Observations of the expanding universe, as described by Hubble's law, support the idea that the universe began from a hot, dense state. The discovery of dark matter and dark energy, which make up most of the universe's mass and energy, also shows that our understanding of the universe is still incomplete. The phrase "something from nothing" might refer to creating something entirely new where there was truly nothing before. But not everyone agrees on what nothing really means. In the end, it's important to be clear about which version of nothing someone is referring to. If something came from nothing, what existed before nothing? Philosophically, the idea of nothing can be even more abstract. Some philosophers argue that true nothingness is an absolute void without any properties or existence. Others suggest that even in a state of nothingness, there must be some potential or possibility that allows something to emerge. None of the evidence from the cosmic microwave background radiation or quantum fluctuations tells us what existed before the Big Bang. One of the most mysterious questions in cosmology is what was there before the Big Bang and what created the singularity that led to it. The Big Bang theory says the universe started from an extremely dense and hot point called a singularity. A singularity is a place where everything we know about space and time breaks down, including the laws of physics. If our normal laws of physics don't apply here, then what rules do? To understand this, let's start with Albert Einstein's ideas. His theory of relativity changed how we view the universe by linking mass and time. According to his theory, time isn't fixed but changes depending on the gravitational fields of objects with a lot of mass. He showed that massive objects, like Earth, can slow down time. Now, if mass can slow down time, imagine what happens in a singularity that holds all the mass of the universe. It would stop time completely. So, according to Einstein, the idea of before the Big Bang doesn't really make sense because time itself didn't exist. The cosmic microwave background radiation is key evidence. It comes from a time about 380,000 years after the Big Bang, when the universe was cooling down and forming hydrogen atoms. Before this 380,000-year mark, the universe went through several stages, starting from the Planck epoch and moving through phases like the Grand Unification, Inflationary, Electroweak, Quark, and Hadron epochs. Each stage saw different particles and forces developing into what we recognize today. When we talk about the universe at such a tiny scale, quantum mechanics takes over from classical physics. This shift led scientists like Stephen Hawking to think about how quantum theory could apply to the whole universe. This is where inflationary quantum cosmology comes in. Unlike classical theories that describe the singularity as a point with zero volume, quantum cosmology introduces uncertainty. This means we can't pinpoint the exact moment the universe was created, and particles can pop in and out of existence from what we call a vacuum. In physics, a vacuum isn't truly empty, but rather a state without particles. According to Heisenberg's uncertainty principle, there's always some fluctuation, so a perfect vacuum with zero field values is impossible. This might sound strange, but Einstein's famous equation, E equals mc squared, helps explain it. The positive energy in stars and galaxies must be balanced by an equal amount of negative energy, like gravity. If the universe's total energy is zero, then it's possible for it to come from nothing. The idea that hundreds of billions of galaxies could come from nothing seems unbelievable. However, Einstein's equation gives us some hints. According to this equation, all the positive energy in stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which appears as gravity. In a closed universe, these positive and negative energies would perfectly cancel each other out, resulting in a net energy of zero for the entire universe. Stephen Hawking asked how a universe with zero total energy could come from nothing. He suggested that gravity's negative energy could balance out the positive energy needed to create matter. This would make empty space stable. Physicist Alexander Vilenkin expanded on this idea, showing that a small, energy-filled vacuum could spontaneously appear from nothing and then expand into the universe we see today. This suggests our universe could have started from a state of nothing where time didn't exist. Another interesting possibility is the multiverse hypothesis, which suggests that our universe is just one of many universes that exist at the same time. In this view, the Big Bang that created our universe might be just one of countless such events happening within a larger multiverse. In the multiverse scenario, new universes could be constantly forming, each with its own unique set of physical laws and constants. These universes could arise from different processes like quantum fluctuations or collisions between higher dimensional membranes in string theory. This suggests that our universe's beginning was just one event in an endless cycle of creation and destruction. Some physics theories suggest there are higher dimensions beyond the familiar three dimensions of space and one of time. These higher dimensions could play a crucial role in how our universe came to be. For example, string theory suggests that the universe is made of one-dimensional strings that vibrate in multiple dimensions. In this framework, our universe could be a three-dimensional brain floating in a higher dimensional space. When these brains collide or interact, events like the Big Bang could happen, creating new universes. So, what was there before the Big Bang? The theories we've discussed suggest that time itself started with the Big Bang, making the concept of before difficult to apply. From singularities to quantum fluctuations, these ideas highlight how amazing and mysterious our universe really is. The Big Bang theory explains how the universe expanded from an extremely hot and dense state, but it doesn't tell us what happened before that moment. According to the theory, time, space, matter, and energy all began with the Big Bang. However, some scientists have ideas about what might have existed before the Big Bang. One interesting idea is the Big Bounce. This theory suggests that the universe goes through cycles of expanding and contracting. So, the Big Bang we know could have been just one of many bounces, with the universe constantly being reborn. Another fascinating idea is the concept of a multiverse. This theory proposes that our universe is just one of many, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another universe entirely. These ideas push the boundaries of our current understanding and venture into speculative territory. They rely on advanced concepts in quantum physics and the still theoretical field of quantum gravity. Scientists are working to connect the dots between quantum mechanics and general relativity to better understand these possibilities. After the Big Bang, the universe continued expanding and cooling. At first, it was just a soup of tiny particles. As it cooled, these particles combined to form the first atoms, mainly hydrogen and helium. While these theories offer exciting glimpses into what might have come before the Big Bang, they remain mostly theoretical, highlighting the deep mystery of our universe's origins. As we look further back in time, we can explore the beginnings of each cosmic structure. Each discovery leads to another question: where did this come from, and how did it form? These questions continue until we reach a point where the only honest answer is, we don't know, police, not yet. With what we do understand, we are then faced with the challenging question: how did all of this come to be? The life we see today is possible because of complex molecules, which originally evolved from the simple atoms found in the periodic table. These atoms are the basic building blocks of all the ordinary matter in our universe. These atoms weren't just there from the universe's beginning. They formed through many cycles of stars being born, living, and dying. Each cycle of stellar life contributed to nuclear reactions that produced these atoms, which were then recycled into newer generations of stars. Without this ongoing process, the creation of planets and the complex chemistry needed for life would not have been possible. To understand how the stars and galaxies we see today came to be, a few key factors had to align. First, gravity plays a major role. It pulls together smaller groups of stars and galaxies to form the large galaxies we see today, sparking new rounds of star formation. For gravity to work effectively, there must be enough mass already clumped together. This is where dark matter comes in. Early in the universe's history, dark matter formed halos that helped prevent newly formed stars from scattering their material back into space. Additionally, the right mix of matter, including atoms, dark matter, and radiation, was crucial. This mix not only created the cosmic microwave background, but also produced the light elements during the early universe's hot, dense phase. The growth of galaxies and star clusters depended on small initial differences in density, often called seed fluctuations, which had to grow under the influence of gravity. Lastly, there must have been processes that initially created these density variations, dark matter, and the first amounts of ordinary matter. To understand how our universe emerged from the chaos of the Big Bang, we need to consider some critical conditions that had to be in place right from the start. The laws of physics, the structure of space-time, and the essence of matter and energy weren't just there. They had to come into existence somehow. Take a close look at this picture. This is Eugene Cernan, the last astronaut from the Apollo program to walk on the moon. But something seems strange. Do you notice it? The night sky looks completely empty with no stars at all. Every photo taken during the Apollo missions shows a sky with no stars. Even though the universe is filled with trillions of stars, the Apollo astronauts said they couldn't see a single star from the moon. This lack of stars has fueled conspiracy theories for years, with some people claiming it proves the moon landing was fake. But the real explanation is much more interesting and goes deeper than any conspiracy theory. So, why does space look empty? This problem was first raised by the German astronomer Johannes Kepler in 1610. Our galaxy, the Milky Way, is huge, with an estimated 100 to 400 billion stars. On top of that, the observable universe has trillions of galaxies, each with trillions of stars. With so many stars in every direction, astronomers wondered why the entire sky isn't bright and full of light. Surprisingly, it's mostly dark, and this question puzzled scientists for centuries. Careful study suggests that the sky should be as bright as the surface of the sun. We should be surrounded by a blinding sea of light. Yet, when we look up at night, we mostly see darkness. This puzzle, known as Olber's paradox, took nearly 300 years to solve. Olber's paradox is based on the steady-state theory. Imagine a universe where everything has always stayed the same and always will. The position of stars, galaxies, everything. This was the main idea behind the steady-state theory, which used to be the most popular explanation of the universe. It said the universe was infinite, without a beginning or end, uniform in every direction, and not expanding. With this theory in mind, astronomers faced a big question. If the universe is full of stars and has always existed, why is the night sky dark? According to the steady-state theory, even the light from the farthest stars should have reached us by now, filling the sky with their glow. One early idea was that maybe the stars are just too far away to affect our night sky. But this didn't make sense with the steady-state model. If the universe is infinitely old, there's been plenty of time for the light from any star to reach Earth, even from the farthest parts of the universe. This light should fill the sky, leaving no dark areas. Johannes Kepler had a different idea to solve the paradox, which went against the steady-state theory. He suggested that the universe isn't infinite. Instead, he thought the stars only spread out to a certain limit, and beyond that, there was just empty space. This idea was interesting, but it raised new questions. How far does this space with stars go, and what's beyond that edge? Kepler's idea of a limited universe had its own issues. If the universe had a boundary, the combined gravity of all the stars and planets could pull everything back together, causing the universe to collapse. Because of these challenges, most astronomers kept believing the universe was infinite. This meant the paradox and the steady-state theory remained unsolved for nearly 200 years. Then, a famous German astronomer named Heinrich Olbers brought attention back to this old question. Why is the night sky dark and looks empty? Since then, Olbers' name has become closely tied to the paradox. At the time, people still believed the universe was unchanging. Olbers suggested a simple idea. If the universe is infinite, it would be full of dust and rocks. These particles could block the light from distant stars, making them look dimmer to us. This cosmic dust and rocks would absorb and block starlight as they move through space. Today, many people still think of it this way, similar to how clouds block sunlight and hide the sky. Just like clouds, cosmic dust and rocks can obscure the light from stars. Olbers' explanation wasn't the whole story. Over time, the dust and rocks blocking the light would heat up and start glowing themselves. This means the universe would still be filled with light, just like before. The dust and rocks would only temporarily block the starlight before releasing it again. So, the total amount of light reaching us would stay the same. So, what actually solves this mystery? It took another 100 years to find the real answer. In 1929, Edwin Hubble used his powerful telescope, hoping to find evidence that the universe was shrinking, which would support the idea of a limited universe like Kepler suggested. But instead, Hubble found that galaxies were moving away from us, and the farther a galaxy was, the faster it seemed to be moving away. This showed that the universe wasn't staying the same or collapsing, it was actually expanding. This discovery led to a new question. What does an expanding universe mean for its beginning? Scientists now believe the universe started as something incredibly tiny and dense. It then expanded rapidly in a process called cosmic inflation. As it expanded, it cooled down, and eventually stars and galaxies began to form. This understanding led to what we now call the Big Bang Theory. Scientists think this all started about 13.8 billion years ago, and it's currently our best explanation for how the universe began. Today, most scientists agree that the universe is around 13.8 billion years old. When we look at light that's 13.8 billion years old, we don't see stars not because the light hasn't reached us, but because we're looking back to a time before stars even existed. The farther we look into space, the farther back in time we're seeing, until we reach what seems like the edge of the universe. This isn't a real edge, but rather the oldest light we can see, known as the cosmic microwave background. It's the leftover glow from the Big Bang. When we use telescopes to look beyond the earliest stars, we see a special type of light. This isn't light from stars, but light left over from the Big Bang. It forms a background glow beyond where the stars are. However, the Big Bang Theory brings up a new issue. It suggests that the universe used to be much brighter, especially during a time called the recombination era. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow from the Big Bang, known as cosmic background radiation, should be very bright. According to Olber's paradox, this bright background should make it hard for us to see any faint stars in the night sky. Since the Big Bang happened 13.8 billion years ago, the universe has followed three main rules as it grows and changes. First, at the beginning, the universe was extremely tiny, very dense, and super hot. Second, just a tiny fraction of a second after it started, the universe began to grow bigger and cooler. Third, and this is really important, the universe will keep expanding and cooling down. Astronomers believe this will continue until the universe becomes so cold that all heat disappears. They call this the heat death of the universe, sometimes also known as the Big Freeze. In this future scenario, the universe will have expanded so much that it has cooled down completely, and all heat energy will be gone. These rules show us that our universe has been getting bigger for the last 13.8 billion years. When the universe started, it was filled with very bright and hot light. As the universe expanded, this light stretched out, turning into longer wavelengths, making it cooler and dimmer. This stretching of light is known as the redshift effect. It's why the cosmic background radiation isn't extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expanding universe solve Olber's paradox. The universe started from a single point and quickly expanded during the Big Bang. Over billions of years, it has cooled down. Because the universe isn't infinitely old, there's a limit to how far we can see into space. The redshift effect also makes the light from distant objects appear dimmer. These factors together explain why the night sky looks dark today. The darkness of the night sky shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe started with the Big Bang and has been expanding ever since. The night sky is a quiet reminder of how the universe began as a very hot and dense place. This understanding not only solves Olber's paradox, but also helps us appreciate how amazing and complex the universe really is. The age of the universe is one of the biggest scientific mysteries. The most widely accepted explanation for how the universe began is the Big Bang theory. According to this theory, the universe started as an incredibly hot and dense point about 13.8 billion years ago. This tiny point contained all the matter and energy that would eventually become everything we see today. Since then, the universe has been expanding, cooling down, and forming structures like galaxies, stars, and planets. Scientists use several methods to determine the age of the universe, including studying the cosmic microwave background radiation, observing the universe's expansion rate, and analyzing the oldest known objects in the universe. One of the most important pieces of evidence for finding the universe's age is the TIMB. Discovered in 1965 by Arno Penzias and Robert Wilson, the TIMB is the afterglow of the Big Bang. It's the leftover heat from the early universe, now cooled down and stretched into microwave wavelengths because of the universe's expansion. The European Space Agency's Planck satellite has provided the most accurate measurements of the TIMB. The data from Planck has helped scientists determine that the universe is approximately 13.8 billion years old. The TIMB gives us a clear picture of the universe when it was just 380,000 years old. By studying tiny differences in the TIMB, scientists can learn about the universe's early conditions and how it changed over time. These variations tell us about the distribution of matter and energy in the early universe, helping us estimate its age. Another method for determining the universe's age involves observing its expansion. In the 1920s, astronomer Edwin Hubble discovered that galaxies are moving away from us. The farther away a galaxy is, the faster it seems to move. This relationship is known as Hubble's law. By measuring the Hubble constant, scientists can estimate the time since the Big Bang, giving us an estimate of the universe's age. The Hubble constant measures how fast the universe is expanding. By determining the Hubble constant, scientists can estimate how long the universe has been expanding since the Big Bang. This involves measuring the redshift of distant galaxies and calculating their distances using various methods, like observing Cepheid variable stars and supernova. However, finding the exact value of the Hubble constant has been tricky. Different ways of measuring it have given slightly different results, leading to what's known as the Hubble tension. Despite this difference, the average value of the Hubble constant, combined with other data, supports the idea that the universe is around 13.8 billion years old. Over time, different methods, including observing Cepheid stars and studying the SIM, have consistently backed up the Big Bang theory and our estimate of the universe's age. Stars also give us clues about the age of the universe. By studying the life cycles of stars, scientists can estimate the ages of the oldest star clusters. One important type of star cluster for this purpose is globular clusters. White dwarf stars, which are the remains of stars that have used up their nuclear fuel, also provide useful age estimates. By analyzing how fast white dwarf stars in globular clusters are cooling down, scientists can figure out how long these stars have been cooling, and therefore how old they are. By studying the light from these stars and comparing it to the models of how stars evolve, scientists can estimate the age of the clusters. Since globular clusters formed shortly after the Big Bang, their ages give us a lower limit for the age of the universe. The oldest globular clusters and white dwarf stars are around 13 billion years old. Since these objects must have formed after the Big Bang, their ages support the estimate of 13.8 billion years for the age of the universe. Another method for figuring out the age of the universe involves radioactive decay. Certain elements, like uranium and thorium, break down at predictable rates. By measuring the ratios of these elements in old stars and meteorites, scientists can estimate how much time has passed since these elements were formed. This technique, called radioactive dating, has provided age estimates that match up with other methods, supporting the idea that the universe is around 13.8 billion years old. Gravitational waves, ripples in spacetime caused by major cosmic events, offer another way to study the universe's history. First detected in 2015 by the LIGO and Virgo observatories, gravitational waves provide a new way to measure the Hubble constant and estimate the age of the universe. By observing mergers of neutron stars and black holes, scientists can use gravitational waves to calculate distances and track the universe's expansion rate. This new approach in gravitational wave cosmology promises even more accurate estimates of the universe's age. According to general relativity, our universe has certain characteristics. It is uniformly dense on large scales, has consistent laws and properties, and the Big Bang happened everywhere at once. These features connect the age of the universe with its expansion history. To determine this, scientists rely on various observations. These observations include direct measurements of the brightness and distance of celestial objects, which help us build the cosmic distance ladder. They also include studies of large-scale structures, galaxy clusters, and baryon acoustic oscillations, as well as fluctuations in the cosmic microwave background, which gives us a snapshot of the universe when it was just 380,000 years old. To sum up, scientists use multiple methods to determine the age of the universe. These include studying the cosmic microwave background, observing redshifts of distant galaxies, analyzing the life cycles of stars in globular clusters, and exploring the effects of dark matter and dark energy. Each method adds valuable information, and together they give us a clearer picture of the universe's age and how it has evolved. Another practical approach scientists use to determine the age of the universe is by studying the brightness and distances of certain stars, known as standard candles. One of the most famous examples is the use of Cepheid variable stars. These stars have a known relationship between their brightness and the period of their brightness variations. By measuring the period of these variations, scientists can determine the true brightness of the star and, by comparing it with its observed brightness, calculate its distance from Earth. This helps in building what's called the cosmic distance ladder, a critical tool in estimating the age of the universe. In addition to Cepheids, scientists use Type I supernova as another kind of standard candle. These supernovae occur in binary star systems, where one star is a white dwarf. When the white dwarf reaches a certain mass, it explodes with a predictable brightness. By observing these explosions in distant galaxies, astronomers can determine the distance to these galaxies and, together with their redshift, estimate the expansion rate of the universe. Another hands-on method is radioactive dating, particularly in old meteorites. Elements like uranium and thorium decay over time at well-understood rates. By measuring the ratios of these elements in meteorites, scientists can estimate how long it has been since these elements were formed, providing a lower limit for the universe's age. These practical techniques, combined with observations of the cosmic microwave background and the study of galaxy redshifts, all link up to provide a consistent estimate that the universe is around 13.8 billion years old. For years, people wondered about the shape of the Earth. Is it flat, round, rectangular, or shaped like a saddle? Today, we know that Earth is roughly a sphere. But have you ever thought about the shape of the universe? Scientists have discovered that the universe is expanding endlessly and not slowing down, but its shape is still debated. There are three possible shapes: flat like a sheet of paper, closed like a ball, or open like a saddle. These shapes aren't just theoretical ideas. They have important implications for what the future of the universe might be like. They can tell us a lot about its past and what could happen next. Will the universe keep expanding forever, start to contract, or is it infinite and limitless? Let's explore what these different shapes mean for the fate of the cosmos. The overall shape of the universe depends mainly on two things: its density and the rate of its expansion. So, is the universe closed, open, or flat? About 2/3 of the universe is made up of dark energy, and just over a quarter is dark matter. The rest is regular stuff we know, like planets and stars. When scientists talk about the density of the universe, they mean how much matter and energy is packed into a given space. If the universe has enough density for gravity to balance its expansion, it would be shaped like a sphere, known as a closed universe. A closed universe would be finite but without any edges, meaning you could travel endlessly without ever hitting a boundary. On the other hand, if the universe doesn't have enough density to stop its expansion, it would be shaped like a saddle, known as an open universe. However, the most reliable scientific data suggests that the universe is flat. In a flat universe, the density is just right, allowing it to expand evenly in all directions without any curvature. What does it mean when we say the universe is flat? This flatness isn't like a two-dimensional surface we're familiar with. Instead, imagine you're standing in one corner of a square room. Walk 10 feet to the next corner along the wall, then make a 90-degree turn. Walk another 10 feet, make another 90-degree turn, and do this 2 more times. You'll end up back where you started, forming a square. This follows the Euclidean geometry we learned in school. Now, if you add an extra dimension to this concept, you get a flat universe. In a flat universe, geometry follows the rules of Euclidean geometry. This means that parallel lines never meet, and the angles of a triangle always add up to 180 degrees. A flat universe can be imagined as a plane that stretches out infinitely in all directions. A flat universe suggests that the amount of matter and energy is exactly equal to the critical density. The critical density is the precise amount needed to make the universe flat. Now, let's think about a positively curved or closed universe. Imagine starting at the equator on Earth and walking to the North Pole. If you turn 90 degrees and walk back to the equator, turn another 90 degrees and return to your starting point, you'll notice that in a closed universe, you'd only need 3 turns instead of 4. To make it even simpler, picture 2 rockets flying side by side. In a flat universe, they would stay parallel forever. In a closed universe, their paths would eventually curve and meet again. In an open universe, they would drift apart and never meet again. One important clue about the shape of the universe comes from the cosmic microwave background, the leftover heat from the Big Bang. Scientists have studied the temperature variations in the CM and found almost no curvature, supporting the idea of a flat universe. However, in 2019, a study suggested that chem measurements might point to a closed universe. This was based on how the chem light bends due to gravity. The amount of bending observed was more than expected, and a closed universe could explain this. But the team behind the measurements didn't think this was a major issue. Some experts believe this could be just a random quirk in the data. Still, these findings are worth paying attention to. It doesn't directly prove that the universe is closed, but it suggests we might be missing something important. Some researchers even call it a cosmological crisis. If the universe were closed, it would clash with other data, making it difficult to accept. If the idea of a closed universe were proven true, it would challenge years of established research. However, there isn't enough evidence yet to question the widely accepted view that the universe is flat. Other TEM measurements and data from telescopes continue to support a flat universe. Additional data, like patterns left on galaxies by ancient sound waves, also back up the idea of a flat universe. Given the strong evidence for a flat universe, most scientists are doubtful of one conflicting result. While the study suggesting a closed universe is interesting, other data continues to support the idea that the universe is flat. Recent research combining multiple datasets found no deviation from flatness, indicating that the observed anomaly could just be a statistical glitch. Other studies have also found similar results, showing that there's no need to change the current cosmological model. For now, it seems the universe acts like a 3-dimensional sheet of paper. While not everyone is completely certain it's perfectly flat, that's how it appears based on current observations. It's important to remember that our view is limited to the observable universe, so there might be things we can't see. If the universe does have curvature, it would have to be so slight that the 93 billion light-years we can observe aren't enough to detect it. To compare it to something familiar, it's like standing in a foggy field where you can only see a small flat area, while the true shape of the land is hidden beyond the fog. When we say the universe is flat, we mean that the part we can observe looks like flat, 3-dimensional space. Another practical method involves looking at distant galaxy clusters and measuring how they are spread across the sky. Scientists use baryon-acoustic oscillations, which are sound waves that leave imprints in the distribution of galaxies. These imprints act as a standard ruler for measuring distances. By comparing the observed distances with what they expect in different types of universe shapes, they can determine whether space is curved or flat. So far, these measurements have strongly supported a flat universe. Additionally, gravitational lensing offers another approach. When light from distant objects passes by a massive cluster of galaxies, it gets bent by gravity. By measuring how much the light bends, scientists can infer the curvature of space. Flat space would produce predictable bending patterns, and the observed data aligns closely with this flat model. When we talk about the edge of the universe, we need to clarify what we mean by edge. In everyday language, an edge is where something ends, like the edge of a table or a piece of paper. But when it comes to the universe, the idea of an edge is much more complex and interesting. The universe includes everything, all space, time, matter, and energy. So, can something that includes everything even have an edge? First, let's think about the idea that the universe might be infinite. If it is infinite, then it has no boundaries and stretches out forever in all directions. In such a universe, it's impossible to point to a center or an edge because every point is just another spot in an endless space. This is similar to the surface of a balloon. As you blow air into it, the balloon expands, and every point on the surface moves away from every other point. But there's no edge on the surface itself. Each point could be considered the center from its own perspective, but there's really no central point. Now, let's consider the observable universe. This is the part of the universe that we can actually see or detect. The observable universe is limited by the speed of light, meaning we can only see light that has had time to reach us since the beginning of the universe, about 13.8 billion years ago. This creates a spherical bubble around us with a radius of about 45 billion light years, known as the cosmic light horizon. Beyond this horizon, light from more distant areas hasn't had enough time to reach us yet, so those regions are invisible to us. The observable universe is like standing in a foggy field with a flashlight. The light only lets you see so far, and beyond that, everything is hidden by the fog. This doesn't mean the field ends where the light stops. It just means you can't see beyond that point. In the same way, the observable universe is limited by how far light has traveled, but the universe likely continues far beyond what we can see. A common misunderstanding is that the edge of the observable universe is the edge of the entire universe. In reality, the observable universe is just a small part of the whole universe, which could be much bigger or even infinite. The cosmic microwave background acts like a wall of light, marking the edge of what we can observe. Beyond this point, we can't see anything directly because the universe was opaque before this time. To understand what might lie beyond the observable universe, scientists use the principle of cosmological homogeneity. This principle says that the universe, on a large scale, is uniform and looks the same in every direction. It suggests that regions beyond what we can see are probably similar to what we see within our observable universe: galaxies, stars, and cosmic structures extending into the unknown. If we could somehow see beyond the cosmic light horizon, we'd likely find more of the same cosmic web of galaxies and empty spaces. Let's imagine traveling to the edge of the observable universe. As we move outward, we would pass through billions of galaxies, each containing billions of stars and countless planets. These galaxies are organized into clusters and superclusters, connected by vast threads of dark matter and gas, forming a complex cosmic web. Eventually, we would reach the cosmic light horizon, where the light from the earliest galaxies has taken billions of years to reach us. At this point, we'd encounter the cosmic microwave background, the faint glow left over from the Big Bang. This cone marks the limit of what we can see directly, but it also gives us valuable information about the early universe and how it's structured. By studying it, scientists have learned that the universe is expanding and have been able to estimate its age, makeup, and shape. But what if we could go even further? Beyond the cosmic light horizon, the universe keeps expanding. This expansion means that distant galaxies are moving away from us faster than light due to the stretching of space itself. This doesn't break the laws of physics because it's space that's expanding, not the galaxies moving through space. If we could travel beyond the observable universe, we would probably find that the cosmic web continues, with more galaxies and structures similar to those we see within our observable limits. The uniformity of the Kiam suggests that the universe beyond what we can see is much like the part we can see. However, since light from those far-off regions hasn't reached us, we can't know exactly what's out there. The idea of an infinite universe opens up some interesting possibilities. If the universe is truly infinite, there could be an endless number of galaxies, stars, and planets. The sheer variety and scale of cosmic objects in such a universe would be mind-blowing. There could be regions of the universe that are vastly different from what we know, with different kinds of stars, galaxies, and even different physical laws. Another interesting idea is the concept of a multiverse, where our universe is just one of many that exist. In this scenario, each universe could have its own unique physical laws and constants, leading to a wide range of possible realities. Some theories suggest that these universes could be connected through wormholes or other strange phenomena, allowing for the possibility of traveling between them. Going back to our balloon analogy, imagine that the surface of the balloon represents our universe. As the balloon expands, new areas of the surface come into view, but the surface itself has no edge. Similarly, as the universe expands, new regions of space become visible, but the universe itself remains endless. Another possibility is the idea of a finite but unbounded universe. In this case, the universe could be curved in such a way that it loops back on itself. This would mean that if you traveled far enough in one direction, you would eventually end up back where you started, similar to traveling around the surface of the Earth. This concept is hard to picture because we usually think in 3 dimensions, but it's a valid explanation in Einstein's general relativity. In such a curved universe, there would be no edge, but the overall shape of the universe would be finite. This idea fits with some interpretations of the cosmological principle, which says that the universe is uniform and looks the same in all directions on large scales, but it could be curved in higher dimensions. Whether this curvature is positive, negative, or flat depends on the overall density and composition of the universe. One of the most important discoveries in cosmology is that the universe's expansion is speeding up. Observations of distant supernova and the SEM have shown that not only is the universe expanding, but it's doing so at an accelerating rate. This acceleration is caused by a mysterious force called dark energy, which makes up about 68% of the universe's total energy. Dark energy has huge implications for the future of the universe. If this acceleration keeps going, galaxies will move away from each other faster and faster, eventually becoming so distant that they will be completely out of sight. Future civilizations in faraway galaxies might never know that other galaxies even exist because they will be beyond the observable horizon. In summary, the edge of the universe is a complex and fascinating idea. Even though we can't see beyond the observable universe, cosmology suggests that the universe continues much the same way beyond what we can see. Whether the universe is infinite or finite, but unbounded, it likely has no physical edge. The universe's expansion, driven by dark energy, means that our view of the cosmos will keep changing, revealing more about its vast and mysterious nature. To better understand the cosmic light horizon, let's talk about some of the oldest objects found in space. These include 3 galaxies, GINS 11, AD 1, and GLASS Z13. GINS 11 is one of the most distant galaxies ever observed. This galaxy is so far away that its light has taken 13.4 billion years to reach us, meaning we are seeing it as it was just 400 million years after the Big Bang. It's also the farthest galaxy ever discovered. Art-1 is another extremely distant galaxy, located about 13.5 billion light-years away. This galaxy is important because it provides clues about how the earliest stars and galaxies formed. Another galaxy is Glass Z13, which has been observed at a distance of about 13.3 billion light-years. Like Haynes 11 and Art-1, this galaxy gives us a glimpse of the early universe. Everything we know, see, observe, and interact with is part of what we call the observable universe. Beyond what we can see, there's likely much more out there. As time passes, we'll be able to see more of it as light from distant objects finally reaches us after traveling for billions of years. Our view of the universe depends on several factors. First, it's been 13.8 billion years since the Big Bang. Second, the speed of light, which is the fastest anything can travel, is finite and constant. Third, space itself has been expanding since the Big Bang. What we see today is a result of these factors combined with the distribution of matter and energy, all following the laws of physics. To understand what the universe was like in the past, we observe it today, measure important details, and use calculations to look back in time. This involves using complex equations, which cosmology students learn to solve. We've made impressive measurements about the universe. We know how fast it's expanding, the density of matter, the amounts of normal matter, dark energy, and even smaller components like neutrinos, radiation, and black holes. By looking at this data, we can figure out how big the universe was and how fast it was expanding at different times in its history. Today, our observable universe extends about 46.1 billion light-years in all directions from us. This distance marks how far light or gravitational waves from the Big Bang would have traveled to reach us now. It's much farther than the most distant galaxy we've discovered. Simulations suggest that the first stars formed between 50 and 100 million years after the Big Bang, and the first galaxies appeared around 200 million years later. We haven't observed that far back yet, but the James Webb Space Telescope might help us soon. The current record holder for the most distant galaxy is Haynes 11, which existed when the universe was 400 million years old, just 3% of its current age. This galaxy is 32 billion light-years away, much closer than the edge of the observable universe. The reason for this difference is that the universe's expansion rate has slowed a lot over time. When galaxy GNZ 11 existed, the universe was expanding 20 times faster than it is today. During the time when the cosmic microwave background was emitted, the expansion was 20,000 times faster. At the moment of the Big Bang, it was even faster. Based on our best theories, the first true galaxies likely formed between 120 and 210 million years after the Big Bang, corresponding to a distance of 35 to 37 billion light-years from us. This shows how quickly the universe expanded in its early stages, with just 1% of its age responsible for 20% of its total expansion. The universe's expansion stretches the light's wavelength, causing the redshift effect that we see. The current size of the universe shows how time affects it. As time moves forward, the universe will keep expanding. In the future, distances will increase so much that no galaxies beyond our local group will be visible, even with the most powerful telescopes. So we should appreciate the diverse and vast universe we can see today, as it won't stay this way forever. To understand what might be outside the edge of the universe, we first need to know the difference between the observable universe and the entire universe. The observable universe is the part of the universe we can see from Earth, limited by the speed of light and how old the universe is. Because light takes time to reach us, we can only observe objects whose light has had time to travel to us since the Big Bang, about 13.8 billion years ago. Cosmologists estimate that the oldest light we can see has traveled between 45 and 47 billion light years from the Big Bang. This means the observable universe has a radius of around 46.5 billion light years. The expansion of the universe has caused distant objects to move farther away, making the observable universe much larger than just 13.8 billion light years. It's also estimated that the diameter of the observable universe is about 93 billion light years. This includes everything visible to us, from tiny particles like quarks to huge structures like quasars, stars, planets, nebulae, and black holes. But keep in mind, the observable universe is limited to what we can see based on the light that has reached us. When people talk about the edge of the universe, they often mean the edge of the observable universe. However, this edge isn't a physical boundary, it's just the limit of what we can see or study. Beyond this limit, the universe still exists, but we can't observe it directly because the light from those distant regions hasn't reached us yet. The universe is likely much bigger than the part we can see and might even be infinite. If the universe is infinite, it stretches out endlessly beyond the observable edge. In this case, asking what exists outside the edge of the universe doesn't make sense because there's no edge, just more universe. But how can the observable universe be 93 billion light years across if the universe is only 13.8 billion years old? This can be explained by a key concept in physics. According to special relativity, objects close to each other can't exceed the speed of light. However, this rule doesn't apply to distant objects when the space between them is expanding. It's not that these objects are moving faster than light, but rather that space itself is expanding, making them move apart quickly. To reach the edge of the observable universe, you'd have to travel faster than light, which is considered impossible by most physicists. Or you'd need to find a way around Spacetime's limits, like through theoretical ideas such as wormholes or warp drives, although these concepts are very speculative. What lies beyond the observable universe is still a mystery, since we can't observe it. However, there are different theories about what might be out there. One simple theory suggests that the space beyond what we can see might just be more of the same cosmic features we see in the observable universe. It's likely that the universe beyond our sight isn't drastically different from what we can observe. It's hard to imagine the universe just stopping abruptly, as if there's a big wall marking the boundary. So, the idea that the universe might be infinite makes sense. If it's infinite, there could be endless stars, planets, and even every possible scenario you can think of. If the universe is truly infinite, it's possible that somewhere out there, there's another person who looks exactly like you and lives a life very similar to yours. There could also be versions of you that are slightly different. Maybe one is a bit shorter, another might have passed away earlier, or one might be missing a finger. It's even possible that this other version of you is watching this video right now. It's a strange idea, but that's how infinity works. Another theory called dark flow was introduced in 2008 when astronomers noticed galaxy clusters moving in the same direction at incredible speeds over 2 million miles per hour. This could be caused by massive unknown structures beyond what we can see, pulling these galaxies with their gravity. These structures could be huge clusters of matter and energy, or strange distortions in spacetime that might even connect to other universes. We really don't know what these massive objects could be. Although some recent studies have questioned the dark flow theory, it's still being debated. There's also the idea of a multiverse, where our universe is just one bubble in a massive sea of other universe bubbles. This theory suggests that these universes could interact, and the gravitational pull between them might cause collisions, possibly leading to events like our own Big Bang. These ideas are just a few of the common theories about what might be beyond the universe we can see. The true nature of what's out there remains one of the biggest mysteries in cosmology, motivating ongoing research and discovery to learn more about our vast universe. Some theories even suggest the existence of extra dimensions beyond the three spatial and one-time dimensions we experience daily. For example, string theory proposes additional dimensions that are too small for us to detect. If these extra dimensions are real, they could hold entire universes with their own physical laws and constants, potentially giving us more clues about the structure and limits of our universe. There's also the cyclic universe theory, which suggests that the universe goes through endless cycles of expansion and contraction. According to this idea, the universe expands to a certain point, then gravity pulls everything back together into a dense state, causing a big crunch that leads to another big bang. This continuous cycle of creation and destruction means the edge of the universe might just be a transition point in an eternal sequence. The universe is expanding, and this expansion affects how far we can see into space. The expansion is driven by dark energy, a mysterious force that speeds up the rate of expansion. As the universe expands, distant galaxies move farther away from us, and the light from these galaxies gets stretched into longer wavelengths known as redshift. The expansion of the universe creates a cosmic horizon, which is a boundary beyond which we can't see. This horizon is determined by the distance that light has traveled since the Big Bang. As the universe continues to expand, the cosmic horizon will shift, potentially revealing new regions of space that were previously out of our reach. This horizon marks the farthest distance light has traveled to reach us since the universe began. Anything beyond this horizon is beyond our reach, hidden away by the limits of light speed and the age of the universe. To understand what might be outside the universe, we need to think about the nature of space and time. According to general relativity, space and time are connected in a four-dimensional continuum called spacetime. The shape of spacetime is determined by the distribution of mass and energy in the universe. If the universe is finite but has no boundaries, the curvature of spacetime could create a closed, self-contained cosmos with no external space or time. In this model, asking what exists outside the universe is like asking what's north of the North Pole. It's a question that might not have any real answer within the laws of physics. The universe is vast and filled with galaxies, stars, planets, and many other celestial objects. However, one of the biggest mysteries in modern science is that about 95% of the universe is missing. The matter we are familiar with, which makes up about 5% of the universe, includes atoms and particles that form stars, planets, and galaxies. Then there's dark matter, which makes up about 27% of the universe. We can't see dark matter because it doesn't emit or reflect light, but we know it's there because of its gravitational effects on visible matter. Dark matter acts like a cosmic framework, shaping how galaxies form and stay together. The idea of dark matter was first suggested in the early 20th century when astronomers noticed something strange. When they looked at galaxies, they found that the mass we could see didn't match the mass needed to explain how those galaxies moved. In the 1930s, Fritz Zwicky noticed that galaxies in the Coma cluster were moving much faster than they should based on visible mass alone. He guessed that there must be some invisible dark matter that was adding extra gravitational pull. Dark matter is a type of matter that doesn't emit, absorb, or reflect light, making it completely invisible. We can only detect it because of the way it affects visible matter, radiation, and the structure of the universe. The most mysterious and hard to understand component is dark energy, which makes up about 68% of the universe. Dark energy is the force that's causing the universe to expand faster and faster, pushing against the pull of gravity. Together, dark matter and dark energy make up almost everything in the universe, influencing everything from tiny particles to massive galaxies. While we don't know exactly what dark matter and dark energy are, scientists are pretty sure they exist. Why? Because dark matter is needed for galaxies to form in the first place. When scientists studied the structure of the universe, they realized that the amount of visible matter isn't enough to explain how galaxies hold together. The gravity from visible matter alone isn't strong enough to form galaxies or complex systems. Without dark matter, stars would likely be scattered randomly instead of gathering into the galaxies we see. This suggests that dark matter acts like glue, holding everything together. Although dark matter is invisible, it can be detected indirectly. In areas where there's a lot of dark matter, light passing nearby gets bent, creating a lensing effect. This bending of light reveals where dark matter is based on its gravitational pull. So, what isn't dark matter? First, it's not just ordinary matter without stars. Regular matter gives off detectable particles, making it visible. If dark matter were just ordinary matter, we would have already seen it. It's also not antimatter. When antimatter meets regular matter, it emits gamma rays. If dark matter were antimatter, we would detect these rays, but we haven't. Dark matter isn't made of black holes either. Black holes are dense objects with a strong influence on their surroundings, while dark matter seems to be spread out across space. The gravitational effects of black holes are different from what we observe with dark matter. Scientists are still testing different ideas and running experiments to figure out what dark matter really is. Even with precise tools like the European Space Agency's Planck spacecraft, we can only detect less than 5% of the total observable universe. For years, scientists have been trying to solve the mystery of dark matter, but so far, we only know it's there because of its gravitational effects on visible matter. British physicist Brian Cox suggests that dark matter could be made up of particles we don't know about yet. But how do we actually find dark matter? Scientists are on the hunt for this mysterious substance using the world's biggest physics experiment at CERN in Switzerland, the Large Hadron Collider. Instead of just trying to detect dark matter, they're attempting to create it from scratch. They do this by smashing known particles together at extremely high speeds, which creates massive amounts of energy. This energy might produce particles of dark matter. When the protons collide, they usually make new particles, but most are lightweight. Occasionally, these collisions create much heavier particles, and those are the ones scientists are hoping to find. The search for dark matter continues in underground labs at CERN and by observing the night sky. Scientists believe they're getting closer to figuring out what it's made of. One of the main candidates for dark matter are weakly interacting massive particles. These particles are thought to interact very weakly with normal matter, making them incredibly hard to detect. Underground detectors are designed to catch these rare interactions and provide clues about dark matter. One interesting piece of evidence comes from gravitational lensing. This happens when light from faraway objects, like galaxies or quasars, gets bent around a massive object, like a galaxy cluster, because of gravity. The amount of bending can show us that dark matter is there, adding to the overall gravitational pull. Astronomers also play a big role in the search for dark matter. By studying the night sky, they look at how galaxies and galaxy clusters move. The way these large structures behave suggests there's more mass present than we can see, and that's where dark matter comes in. For example, when astronomers look at how fast stars orbit around the center of galaxies, they notice that there must be extra invisible mass, likely dark matter holding everything together. Even though we haven't directly found dark matter yet, every experiment brings us closer to understanding this mysterious part of the universe. Dark energy is even more mysterious than dark matter. It's a type of energy that we can't directly detect or measure, but we can see its effects. Unlike dark matter, which clumps together due to gravity, dark energy is spread evenly across space. In 1929, astronomer Edwin Hubble made a huge discovery. He noticed that light from distant galaxies shifts towards the red end of the spectrum as it travels through space. This effect, called redshift, revealed something surprising. Hubble found that more distant galaxies showed more redshift, while closer ones showed less. He figured out that this redshift happens because the universe is expanding. As light stretches out, it shifts towards the red part of the spectrum, showing that space itself is getting bigger. Recent discoveries have taken Hubble's findings even further. The universe isn't just expanding, it's speeding up. Scientists used to think that gravity would eventually slow down this expansion or even reverse it. But now they know that dark energy is driving this rapid expansion, pushing the universe apart faster and faster. Space itself doesn't change as it expands. New space is constantly being created everywhere. Galaxies stay held together by gravity, so we don't feel this expansion in our daily lives. But we see it happening all over the universe. Wherever there's empty space, more is being created every second. So, what exactly is dark energy? It seems to be some kind of energy in empty space that's stronger than anything else we know and keeps growing. Empty space contains more energy than everything else in the universe combined. This mysterious force is pushing galaxies apart and making the universe expand even faster. Dark energy remains one of the biggest mysteries in cosmology. While we can't directly detect or measure it, its impact on the universe is clear. As we keep exploring and studying the cosmos, we hope to uncover the secrets of this strange force and get closer to understanding the true nature of our expanding universe. The discovery that the universe expansion is speeding up points to dark energy at work. Figuring out what dark energy is remains one of the biggest challenges in cosmology today. Have you ever looked up at the stars and wondered if the entire universe was made just for us? It's a question that has fascinated humanity for centuries. The idea that everything from the galaxies to the tiniest particles exists with us in mind can be both comforting and mind-blowing. But is there any truth to it, or is it just wishful thinking? One of the reasons people ask this question is because of something scientists call fine-tuning. The universe seems to be set up in a very specific way that allows life, as we know it, to exist. The strength of gravity, the charge of electrons, and even the way stars burn are all balanced perfectly. If any of these were slightly different, life might not be possible. This has led some to wonder, did someone or something design the universe with us in mind? This idea brings us to what scientists call the anthropic principle. In simple terms, it says that the universe is the way it is because we are here to observe it. Think about it like this. If the universe weren't set up in just the right way, we wouldn't be here to ask these questions. Some people see this as evidence that the universe is fine-tuned for life, while others think it's just a natural outcome of the conditions we find ourselves in. There's another idea that challenges the thought that the universe was made just for us, the concept of multiple universes. Some scientists believe that our universe is just one of many. In these other universes, the laws of physics could be totally different, making life impossible in most of them. We just happen to live in the one that supports life. If that's true, it might not be so surprising that our universe seems so perfectly balanced it's just one lucky roll of the dice. The search for extraterrestrial life also plays a role in this discussion. If we find life beyond Earth, whether it's tiny microbes on Mars, hidden in the oceans of moons like Europa or Enceladus, or on distant exoplanets, it would show that life isn't unique to Earth, but can emerge wherever conditions are right. Such discoveries would change our understanding of how common life might be in the universe. Philosophical perspectives also shape how we think about this question. Some people find comfort in believing the universe has a purpose, while others see beauty in its randomness and endless possibilities. Whether or not the universe was created with a goal in mind, our natural curiosity and drive to explore are core parts of what it means to be human. Asking these deep questions not only pushes science forward, but also helps us better understand the universe. Science shows the universe as vast and seemingly indifferent, which can make us feel small. Yet, some people argue that we might still have a special role in the universe because of how finely tuned the laws of physics are to allow life. For example, the specific strength of the electromagnetic force is crucial for stars to produce carbon, which is essential for life. Even the energy in empty space seems adjusted to allow intelligent life to develop. This apparent fine-tuning has led to different interpretations of the anthropic principle. One view is that the universe was intentionally designed for us, possibly by an intelligent creator. Another idea, called the life principle, suggests that life is a natural feature of the universe. However, these views aren't widely accepted in the scientific community. Another philosophical take on the anthropic principle is that the universe exists because we're here to observe it. A more practical view is that the universe seems suited for our existence simply because we live in a region that supports life. This could be explained if there are multiple universes, each with different physical laws, and ours just happens to be one where life can thrive. Our universe holds a mystery that has always fascinated people, a question that connects what we know with what we don't, and what is simple with what is complex. Here on Earth, life exists in a balance of order and chaos. Every living thing shows signs of an underlying pattern, from tiny microbes to large mammals. But what if the complexity of life, the core of our existence, could be explained not just through biology, but through maths? This is where assembly theory comes in a new concept that goes beyond traditional science. It takes us into a world where maths and biology work together to uncover the hidden structure of life. Imagine a universe where the secrets of life, from the simplest molecules to the most complex organisms, are written in the language of maths, just waiting to be understood. In this view, the line between what is living and non-living becomes blurred, opening up new ideas and possibilities. Let's explore how this idea is changing how we see life, evolution, and the universe. Maybe it can even help us answer the ultimate question: what is the true nature of life in the universe? Since ancient times, maths has been the language we use to understand nature. But how does maths relate to understanding life itself? Assembly theory offers a simple yet powerful idea. The complexity of life can be measured and understood through maths. Think of life as a jigsaw puzzle, where each piece is a molecular building block. Assembly theory shows how these pieces come together, step by step, to form the complex structures we see in living things. Each step in this process is a move from simple atoms to more complex proteins. The theory introduces the idea of the assembly index. The assembly index, a key part of this theory, measures the number of steps needed to create a biological structure. It's a number that captures the complexity of life by giving us a way to measure what seems unmeasurable. But how does this connect to the standard model of physics? The standard model describes the basic particles and forces that make up our universe. At first, this seems far removed from the complexities of biology. However, assembly theory links the two. The standard model provides the foundation for understanding the forces and interactions that assembly theory builds upon. It connects the tiny particles like quarks and leptons to the bigger world of living things. Another important part of the theory is using phase space, a mathematical concept that shows all the possible states of a system. In assembly theory, phase space helps us map out the pathways of life's development. from a single point representing the simplest form of life to a space that spreads out into almost endless possibilities. Each pathway represents a different direction that life could take. In this vast mathematical landscape, the paths of evolution and its complexity take shape. This mathematical view gives us a fresh way to look at the complexity of life. It's not just about the particles and forces described in the standard model, but also about how these elements come together and interact over time to create the variety of life we see. This is where the randomness of molecular interactions turns into the order we find in living things. We live in a world with 3 dimensions, up and down, left and right, and forward and backward. These are the directions we can move in. Time is another dimension we experience, moving from the past to the future. Together, these make up what we call spacitime. In physics, dimensions are like different directions you can move in, similar to lines on a graph. Normally, we only notice 3 dimensions. But what if there are more dimensions that we can't see? Theories like string theory and M-theory suggest there might be extra dimensions. According to string theory, the smallest parts of our universe are not tiny points but small, vibrating loops of energy called strings. The maths behind string theory suggests that there need to be 10 or 11 dimensions for everything to work correctly. String theory tries to explain all the natural forces, like gravity, electromagnetism, and the forces inside atoms, by saying everything is made of these strings. The way these strings vibrate determines the type of particles they become. So why can't we see these extra dimensions? They might be incredibly small and tightly folded up, making them impossible to detect with our current tools. For example, imagine an ant walking on a tightrope. To the ant, the rope looks like a line because it can't see its width. Similarly, these extra dimensions could exist but be too small or hidden for us to notice. If these higher dimensions are real, they could help us solve some big questions in physics, like why gravity is much weaker than other forces. Maybe gravity spreads out into these extra dimensions, making it seem weaker in our 3-dimensional world. These higher dimensions could help us better understand particles and forces. They could connect all the different forces into one complete picture, leading to new technologies and a deeper understanding of the universe. Scientists are looking for evidence of these higher dimensions. One way is by studying how gravity behaves at very tiny scales. If higher dimensions are real, they could cause slight differences in gravity, which we might notice in lab experiments. Another method involves high-energy particle collisions, like those at the Large Hadron Collider. In these experiments, particles are smashed together at high speeds. If any particles disappear into higher dimensions, it could be a clue that these dimensions exist. There are also other interesting ideas about higher dimensions. For example, some theories suggest our universe might be a 3-dimensional brain floating in a space with more dimensions. In this idea of a brain world, our universe could be just one of many parallel universes, each existing as a separate brain in a space with extra dimensions. This raises exciting possibilities about how these universes might interact, like through gravity or by exchanging particles. Another idea connected to higher dimensions is the multiverse theory. This theory suggests that our universe is just one bubble in a vast space full of other universes, each existing in a higher dimension. These different universes could have their own physical rules and might even interact with each other. For example, if these universes collide, it could create a massive explosion like the Big Bang that started our universe. While the idea of higher dimensions is fascinating, it remains a theory. One of the biggest challenges is that these dimensions are not something we can currently see or measure directly. To detect them, we would need extremely high energy or very precise measurements, which are beyond what we can do with today's technology. Mathematics plays a key role in helping us explore the concept of higher dimensions. Many of the theories suggesting the existence of these extra dimensions rely on complex maths from areas like geometry, topology, and algebra. These branches of maths help us imagine and understand spaces that go beyond the three dimensions we usually think about. Mathematicians and physicists work together to create models that predict how these higher dimensions might affect what we can observe in the universe. They then test these models with experiments and observations. Quantum mechanics, which studies how particles behave at very small scales, could also be influenced by higher dimensions. The strange and often confusing behaviors we see in quantum mechanics might be due to interactions happening in spaces with more than three dimensions. So, do higher dimensions really exist in the universe? While we don't have concrete proof yet, the possibility of higher dimensions is an exciting area of research in theoretical physics. If these dimensions are real, they could change how we see the universe and reveal new insights about the nature of reality. Studying the whole universe is one of the most ambitious and exciting goals in science. The universe is incredibly vast, spanning billions of light years and filled with galaxies, stars, planets, and many other celestial objects. To understand its structure, origins, and future, scientists use a variety of tools and methods. Let's explore how we study the universe, from telescopes that capture its light to the theories that help explain its mysteries. Telescopes are the main tools astronomers use to study the universe. They help us see distant objects by collecting and magnifying their light. There are different types of telescopes, each designed to capture various wavelengths of light and other forms of energy. Think of the universe as a pie chart with different slices representing different components. First, we have normal matter, which makes up only 5% of the universe. This includes atoms that form stars, planets, and everything we see around us. Next is dark matter, a mysterious type of substance that accounts for about 25% of the universe. Scientists estimate the amount of dark matter by studying small temperature changes in the cosmic microwave background. These estimates match what we observe from the movement of stars and galaxies. The CME comes from a time when the universe had cooled enough to let photons escape from the hot plasma that trapped them for hundreds of thousands of years after the Big Bang. This confirms that dark matter was already present in the early universe. Normal matter makes up only a small portion of the total mass of the universe. Then there's dark energy, a strange force that's driving the rapid expansion of the universe. It makes up 70% of the universe's total matter and energy. We also have the optical layer, which shows us how much the universe absorbs and scatters light, especially photons. This layer helps us understand the processes behind the birth and explosive deaths of the first stars and the formation of the earliest galaxies. When these stars and galaxies formed, they emitted strong radiation that broke hydrogen atoms into protons and electrons. This event, called reionization, caused about 5 to 8% of the CME photons to scatter again. You can think of it as a light mist appearing in a previously clear universe, making it slightly harder to see. To measure this depth of the universe, scientists study the polarization of the CME. This gives us clues about the early stages of the universe and helps us piece together the story of how the first stars and galaxies formed. When exploring the universe, we also consider polarization, which is one of the three features of a light wave, along with intensity and wavelength. Some of the changes and structures in the universe are described by the primordial power spectrum, which shows variations in the universe's density. In the early universe, these differences were small, but as time passed, they became more noticeable. The scalar spectral index helps us understand how these early fluctuations developed. Using these 6 parameters, we can calculate not only the properties of the SIEM, but also other measurements in cosmology. For example, we know the universe is about 13.8 billion years old, with an accuracy of 40 million years. The most precise data comes from studying the small temperature variations in the SIEM. The standard cosmological model fits well with all observations across different fields of science, including physics and astronomy. One of the most important tools for exploring the universe is the telescope. From early models to today's advanced ones, telescopes let us observe distant objects in space, like planets, stars, galaxies, and nebulae. Different telescopes are designed to see different types of light, such as visible light, radio waves, and X-rays. Optical telescopes, like the Hubble Space Telescope, capture light we can see and give us amazing images of far-off galaxies and nebulae. Radio telescopes, like the Arecibo Observatory, pick up radio waves from space, helping us study things like pulsars and black holes. X-ray telescopes, like the Chandra X-ray Observatory, look at high-energy events such as supernova and the areas around black holes. Besides telescopes, scientists use space missions to explore the universe. Space probes and satellites travel beyond Earth's atmosphere to get a clearer view of the cosmos without the interference of our planet's atmosphere. For example, the Voyager probes, launched in the 1970s, have traveled beyond our solar system, sending back information about the outer planets and the space between stars. The New Horizons mission gave us our first close-up pictures of Pluto and is now exploring the Kuiper Belt. The James Webb Space Telescope is the most advanced telescope yet, allowing us to study exoplanets and distant celestial objects. A key method for studying the universe is by examining the cosmic microwave background. The CMB is leftover radiation from the Big Bang and gives us a glimpse of what the universe looked like when it was just 380,000 years old. By analyzing the CMB, scientists learn about the early conditions of the universe, its makeup, and its age. The Planck satellite created the most detailed map of the CMB, showing tiny variations that reveal how matter and energy were distributed in the early universe. Scientists also conduct large-scale galaxy surveys. These surveys map the positions and characteristics of millions of galaxies, revealing the cosmic web, a massive network of galaxies and dark matter that stretches across the universe. The Sloan Digital Sky Survey is one of the most detailed galaxy surveys, mapping millions of galaxies and helping us understand the universe's large-scale structure, how it's expanding, and where dark matter is located. While observations provide data, theoretical models and simulations help scientists understand that data and predict how the universe behaves. These models are based on the laws of physics and are tested against real observations. Albert Einstein's theory of general relativity explains how gravity works on large scales. It's been crucial in understanding the expansion of the universe, black holes, and how light behaves near strong gravitational forces. The Big Bang Theory is the main idea for how the universe began, explaining how it expanded from a super-hot and dense state to what we see today. Supercomputers are used to run detailed simulations of how the universe has evolved from the Big Bang to now. These simulations help scientists study how galaxies form, how dark matter acts, and how dark energy affects the universe. Studying the universe is a huge task that requires advanced technology, creative ideas, and teamwork across the world. Telescopes on Earth and in space collect data to observe the cosmos. Surveys map the large-scale structure of the universe, while models and simulations help explain the data and predict what's happening. In 1980, a mathematician named Benoit Mandelbrot was one of the first to use computers to visualize ideas that were too complex to draw by hand. He used simple equations to create images of a new kind of geometry called fractals. The word fractal comes from a Latin word that means broken or shattered glass. Fractals are patterns that look similar no matter how much you zoom in or out, always showing more detail and never becoming simpler. This makes them endlessly complex. Mandelbrot created what we now call the Mandelbrot set to show this idea, but he also noticed that similar patterns exist in nature, like in fern leaves, broccoli, and even the way galaxies are arranged. He wondered if the entire universe might be a fractal, although today we know that at the largest scales we can observe, the universe looks mostly uniform. But could there be fractal-like patterns beyond what we can currently see? While we may not yet know how far the universe stretches beyond what we can observe, even looking at what we can see brings us back to the idea of infinity. Our universe is expanding, with everything moving away from everything else, like dough rising in an oven. If the universe started from an infinite point, our observable universe would just be a small part of that endless space. Over time, although what we can see expands, it's really just a measure of how far light has traveled since the beginning. The physical universe is becoming less dense as it expands. While larger structures like galaxies stay together due to gravity, every galaxy beyond our local group is drifting away at an average speed of 70 kilometers per second, a megaparsec. Looking ahead, if nothing new happens, the universe will keep expanding. Galaxies will move farther apart, stars will drift away from each other, and the universe will reach a state known as heat death. However, there is no single moment when the universe ends. Our observable universe will continue growing, possibly becoming infinitely large. Because infinity has no end, it would take an infinite amount of time to reach this state, and we could still only explore a small part of it, since the universe expands faster than we can explore it. When we look back in time, the universe shrinks, becoming denser and hotter until it no longer looks like the universe we know today. At this point, the laws of physics behave in strange ways. We can only begin to understand the universe when it becomes larger than 1 Planck length. Below this size, our current physics stops working. The universe may have started expanding from a point that was infinitely small, dense and hot. We don't know what that would look like or how it would behave. Our observations don't suggest any other kind of beginning. Thinking about the universe being infinitely old and expanding from something infinitely small is a challenge to our understanding. Based on what we currently know, we can't disprove the idea that the universe could keep expanding forever. This raises questions about how we reconcile the Big Bang theory with the idea of an infinitely large universe. The universe we observe is expanding, but that might not be true for the entire universe all the time. Cosmologists like Alan Guth and later Andre Linde suggested that what we see could be just a small, expanding region within an infinitely large universe. This idea, called eternal inflation, proposed in 1979, suggests our universe is just one of many bubble universes in an endless cosmic space. Each bubble universe could be at a different stage of development and might even have different physical laws. This leads to the concept of a multiverse, where endless universes exist, each with its own rules. Exploring these ideas adds even more complexity, especially when we consider theories like M-theory. This theory suggests our universe is just one of many layers, existing briefly where different dimensions intersect within a vast higher dimensional space. We then have to think not only about infinite universes in our 3 dimensions, but a multiverse with countless dimensional combinations. Each of these universes could have different constants, like gravity or particle mass, leading to endless possibilities. Our Big Bang could be just a tiny event, and the heat death of our universe just one large event in a much bigger picture. Research suggests that our universe might be just one bubble among many in a vast sea of universes, each with its own physical laws that could be completely different from ours. British physicist Brian Cox has talked about how the idea of multiple universes fits within a concept called eternal inflation. In this theory, our universe is just one bubble in a frothy space-time filled with other bubbles. These bubble universes are constantly forming. The process starts when a certain region of space stops expanding rapidly, but not all regions of space stop inflating at the same time. Some parts continue expanding, leading to the ongoing creation of new universes. Each universe can have its own unique physical laws, possibly very different from what we know. To better imagine this idea, think of an enormous library with countless books. Each book represents a different universe. If the library has an infinite number of books, then every possibility exists in one of them. In one book, gravity could be weaker, allowing creatures to grow taller and buildings to be much higher. In another book, the speed of light could be slower, changing how light and energy work. But these differences between universes aren't just about physical laws. They could include completely different histories and evolutions. Picture a universe where dinosaurs never went extinct and evolved into the dominant intelligent species. Or imagine a universe where the basic elements of matter are different, leading to planets and stars made from dark matter instead of the substances we know. Is there any evidence that a multiverse exists? Could our universe be just one bubble in a larger multiverse? In the book Endless Universe, Beyond the Big Bang, authors Paul Steinhardt and Neil Turok present an interesting idea. They suggest that the universe didn't start with just one Big Bang. Instead, they propose a model where cosmic events happen in cycles, which could even involve our universe colliding with other bubble universes. This idea aligns with findings by researcher Ranga Ramchari in 2015. He proposed that our universe might have bumped into another universe. His study of the cosmic microwave background revealed unusual signals that could hint at such a cosmic interaction. However, it's unclear whether this contact was minor or significant. The CMB is often called the afterglow of the Big Bang and is the oldest light we can detect with modern instruments. It's like a picture of the early universe from billions of years ago, helping scientists understand how the universe expanded and developed. Some scientists think the CMB might hold clues about the existence of a multiverse. When astronomers study the CMB, they don't just see a smooth glow. They find a pattern of light and dark patches showing tiny temperature differences that shaped the universe's large-scale structure. One mysterious feature within the CMB is the cold spot, a large area with lower than average temperatures. An interesting theory about the cold spot is that it might be a cosmic bruise left behind when our universe brushed up against another universe. This idea supports the concept of a multiverse, where multiple universes exist and sometimes interact. In 2007, theoretical physicist Laura Massini-Houghton and her team proposed that the cold spot might be evidence of our universe interacting with another one. According to their theory, if multiple universes exist, they might occasionally collide, leaving visible marks like bruises. Massini-Houghton suggests that the cold spot is one such bruise caused by the gravitational pull of a neighboring universe. This pull could have slowed down the expansion in that part of our universe, leading to the cooler temperatures we see today. This theory connects with Ranga Ramchari's 2015 study, which also suggested that unusual features in the CMB could be signs of a past collision with another universe. Both ideas point to the possibility that interactions between universes might leave detectable scars or dents in the fabric of our universe. Over time, these ideas have led to predictions about what other similar anomalies might look like. According to the theory of cosmic inflation, everything in the universe should be spread out evenly across the sky. But anomalies like the cold spot challenge this idea, hinting that our universe's history could be more complex than we once thought. These observations and theories raise deep questions about our universe. They challenge the traditional view that the Big Bang was the absolute beginning. Instead, they suggest that the Big Bang could have been a transition from a previous universe, or that the universe might have existed in some form before what we think of as the beginning. The unusual features seen in the STEM suggest that our understanding of the universe's origin might need to be updated to include these new ideas. In 1950, the well-known physicist Enrico Fermi asked a straightforward yet significant question during a lunch with his colleagues. If the galaxy is so vast, where are all the advanced alien civilizations? This question is now known as the Fermi paradox. The paradox arises because, given the countless stars and planets in our galaxy, which is around 400 billion stars, it seems likely that some of these planets should have intelligent life. If that's the case, these civilizations would have had plenty of time to explore and even reach Earth. But we have no clear evidence that this has happened. To explain why we haven't found any signs of extraterrestrial civilizations, despite the high likelihood of their existence, several theories have been proposed. Travel is expensive. Traveling between solar systems might be extremely costly and require huge amounts of resources. For example, sending a spaceship to even the closest star would take an enormous amount of energy and money, making it impractical. Limited expansion. Even if a civilization begins exploring and colonizing other planets, maintaining that expansion across generations is tough. The effort needed to continue moving from one star system to another might be too challenging to sustain. We're in a quiet zone. It's possible that the galaxy is full of activity in other regions, but we're simply in a quiet area where not much happens. Cosmic zoo theory. Another idea suggests that Earth is like a zoo or nature reserve, where aliens are observing us from afar, making sure we remain unaware of their existence. To understand where the Fermi paradox comes from, we need to look at two important ideas. The first is the Drake equation, created by Frank Drake, who was a major figure in the search for alien life. This equation suggests there could be thousands of civilizations in our galaxy capable of sending us signals. The second idea is the Fermi paradox, which asks why we haven't found any clear signs of intelligent aliens, like evidence of space travel between stars. The name Fermi paradox is a bit misleading. It was named after the physicist Enrico Fermi, but he never actually created this theory. Even so, the idea is important when discussing the possibility of alien life and has influenced research funding. For example, it played a role in Senator William Proxmire's decision to stop funding NASA's SETI program in 1981. Although Carl Sagan managed to briefly revive the program, it was shut down again in 1993 by Senator Richard Bryan. However, the search for alien life hasn't ended. While NASA doesn't fund SETI the way it used to, research still continues through other sources. The SETI Institute, a private non-profit organization, continues the work. The institute partners with universities, companies, and even government agencies, including NASA, to keep searching for signs of extraterrestrial life. Interestingly, the term Fermi paradox didn't actually come from Fermi. What we know about his thoughts comes from a 1950 lunch in Los Alamos, as recalled by physicist Eric Jones, who interviewed three of Fermi's colleagues, Emil Konopinski, Edward Teller, and Herbert York. During this lunch, Fermi wondered about space travel. This conversation eventually led to what is now called the Fermi paradox. According to Teller and York, Fermi was more interested in whether traveling between stars was possible, not whether aliens exist. The Fermi paradox is usually taken to mean there's no evidence of extraterrestrial life, but this wasn't Fermi's main concern. His doubts were more about whether space travel was achievable, which made sense in 1950 when rockets couldn't even reach orbit, let alone other planets or stars. The idea that no aliens on Earth means no aliens anywhere was first introduced by astronomer Michael Hart in 1975, not by Fermi. Michael Hart argued that if intelligent aliens existed, they should have already colonized the Milky Way. Since we haven't seen any evidence of them on Earth, he suggested that humans might be the only intelligent beings in our galaxy. He even believed that searching for alien civilizations could be a waste of resources. However, many people disagree with his conclusion. They point out that space travel might be impossible. Aliens might choose not to colonize other planets, or they might have visited Earth long before humans existed, leaving no traces. Despite these criticisms, Hart's idea is still widely discussed when talking about extraterrestrial life. In 1980, physicist Frank Tipler expanded on Hart's ideas by addressing the huge resources needed to explore billions of stars. Tipler suggested the idea of self-replicating robots with human-like intelligence. These robots could be sent to a nearby star, use local resources to create copies of themselves, and those copies could continue spreading across the galaxy. Tipler concluded that since we haven't found any of these advanced robots on Earth, it could mean we're the only intelligent civilization not just in the Milky Way, but in the entire universe. This is a bold claim based only on the fact that we haven't encountered aliens yet. What we now call the Fermi paradox mostly comes from the ideas of Hart and Tipler, but over time, their theories have been mixed up with Fermi's original question, causing some confusion about the paradox origins. This confusion likely began in 1977 when physicist David Stephenson used the term Fermi paradox in a publication, presenting Hart's theory as a response to Fermi's question. A more accurate name for this idea could be the Hart-Tipler argument against the existence of technological extraterrestrials. Although this name isn't as catchy as the wrongly attributed Fermi paradox, it would better recognize the true originators of the concept. The search for alien life is still a major focus for scientists. The James Webb Space Telescope is providing us with amazing new images and data, while Mars rovers are studying the planet up close. There are also plans for future missions to explore the farthest parts of our solar system. The question of whether we are alone in the universe remains unanswered, and until we find out, the search for extraterrestrial life will stay a top priority for humanity. Scientists have developed different ways to look for life beyond Earth. A key area of research is studying exoplanets, which are planets that orbit stars outside our solar system. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, some of which are in the habitable zone, where conditions might allow life. The habitable zone is the region around a star where temperatures could allow liquid water to exist. Since liquid water is essential for life as we know it, these exoplanets are top candidates for further study. For life to exist, certain ingredients are needed. Besides liquid water, life requires key elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are the building blocks of organic molecules, which make up all known life forms. Interestingly, these elements are common in the universe. They've been found in interstellar clouds, comets, and even on other planets and moons in our solar system. Scientists are also searching for biosignatures, which are signs of life that can be detected from far away. Biosignatures could include specific gases in a planet's atmosphere, like oxygen or methane, that might indicate the presence of life processes. Another interesting area of research is the search for technosignatures, which are signs of advanced civilizations. This includes looking for radio signals, laser pulses, or other kinds of technology that might suggest intelligent life. Projects like the SETI have been scanning the skies for decades, hoping to pick up a signal from an alien civilization. While searching for life outside Earth, scientists are also exploring the possibility of life within our own solar system. Moons like Europa and Enceladus, which have oceans beneath their icy surfaces, are especially interesting. These oceans could have the right conditions for life, shielded from space by a thick layer of ice. As technology improves, our ability to search for extraterrestrial life will continue to get better. New telescopes, space missions, and artificial intelligence will boost our chances of detecting and studying possible signs of life. We've discovered over 4,000 exoplanets orbiting other stars, and we now know that almost every star has at least one planet. About 1/5 of these stars have Earth-sized planets orbiting them. With around 100 billion stars in the Milky Way, there are likely billions of Earth-sized planets out there. Thinking that only one of these planets has life seems unlikely given the odds. Given the huge number of Earth-like planets just in our Milky Way galaxy, we have to ask, are we really alone in the galaxy? The Hubble Space Telescope has shown us about 100 billion galaxies. Each of these galaxies has around 100 billion stars. Altogether, that's roughly 10,000 billion stars in the visible universe, a number that's hard for us to even imagine. Given the sheer size of the universe, the chances of life existing elsewhere seem pretty high. Consider just how big our universe is, packed with an enormous number of stars. Even in our own Milky Way, which has 100 to 400 billion stars, it seems unlikely that Earth is the only place with intelligent life. The massive number of stars suggests that life somewhere else in the universe is almost certain. Frank Drake was a scientist who tried to figure out how many civilizations might exist in our galaxy that we could detect. He came up with a series of questions that, when combined, give us an estimate. This set of questions became known as the Drake equation, which helps predict the number of detectable civilizations in the Milky Way. For over 60 years, the Drake equation has been our main tool for estimating how many civilizations could be out there, with numbers ranging from 1,000 to 100 million planets hosting civilizations. In the Drake equation, R is the rate at which new stars are formed in our galaxy each year. Then V is the percentage of these stars that have planets. Next, we look at N, which estimates how many of these planets are in the habitable zone, where life could exist. This part is still mostly unknown since we don't know much about planets beyond our solar system. The number 4 tries to figure out how many of these planets actually have life. Then, Phi estimates how many of those planets develop intelligent life. When Frank Drake created his equation, he focused on radio astronomy. He wanted to know how likely it was that alien civilizations were sending signals we could pick up with our technology that is represented by phi in his equation. Back in the 1960s, many scientists believed radio waves were the most likely way advanced aliens would communicate. Earth has been sending radio signals into space for nearly 100 years, reaching stars within an 80 light-year radius. But a big question remains: would aliens in other parts of the universe still use radio waves, or would they see them as outdated, like how we think of smoke signals? The last part of the Drake equation will estimate how long a civilization would be detectable across the galaxy. Drake was concerned that even if a society developed advanced technology, their detectable signals might only last a short time. So, even if civilizations last for thousands of years, we might only catch a brief signal from them. When Drake first did his calculations in 1961, he estimated there could be 4 to 10 detectable civilizations in our galaxy. But using today's scientific knowledge to update those numbers gives a much different result. The new estimate for n, the number of detectable civilizations, is about 0.00127. This means that in every 100,000 years of our galaxy's history, roughly 127 civilizations might become detectable. Drake's belief that there could be around 10,000 civilizations in the Milky Way paints a picture of a busy galaxy. But the challenge of finding even one among 100 billion stars shows just how difficult this task is. To make any claims about how common or rare these civilizations are, astronomers might need to study 10 million stars. This highlights the enormous effort required. We still don't know how many alien civilizations could be out there. Estimates range from just a few to as many as 100 million in the Milky Way alone. But some people think we might be the only advanced civilization in our galaxy. That doesn't mean we're alone in the entire universe, which is incredibly vast. The observable universe spans about 92 billion light-years and has anywhere between 100 billion and a trillion galaxies, each with around 100 billion stars. So, there's a good chance that intelligent life exists somewhere, just maybe not in our Milky Way. Over Earth's history, more than 10 billion species have existed, but none have shown the intelligence, curiosity, and ability to create complex tools like humans. Even smart animals like whales and dolphins don't seem to think deeply or make complex tools. Humans have only been around for a few 100,000 years, so for most of Earth's history, an alien looking at our planet wouldn't see any advanced technology or signs of high intelligence. Also, it's not clear if being so smart is even good for us in the long run. While our intelligence has made life better for many people, it has also brought us close to self-destruction. Recently, astronomers have been trying to get better estimates of how many alien civilizations might be in our galaxy. They're focusing on two big questions: how likely it is for life to start on Earth-like planets from non-living materials, and what the chances are that this life becomes intelligent. Even with these estimates, there's still a lot of disagreement. Some scientists argue that with so many Earth-like planets, we can't be the only ones. Others want solid proof and ask, if there are so many civilizations out there, why haven't we found any evidence of them? This is the big question behind what's known as the Fermi paradox. If alien life is common, where is everybody? SETI, the search for extraterrestrial intelligence, has been actively scanning the sky. But we've only looked a few hundred light-years away, which is just a tiny part of our galaxy. If the galaxy was full of life, especially advanced life, some of it would be much more developed than us. Stars in our galaxy went through processes billions of years ago that created the elements needed for Earth-like planets. So there could be civilizations out there that are billions of years more advanced than us. Considering how fast human technology has developed in just a few hundred years, imagine what a civilization could achieve in thousands or even millions of years. Such civilizations could potentially travel between stars and colonize the galaxy. In theory, they could fill the entire galaxy in just a few million years. If they existed, we might expect them to have reached us by now.